Welcome back to r2con 2020. This is the fourth day of the conference, which is actually the last one. We started the last day with R2 Wars competition. This is the last round. This means that the first three winners of this competition will be the actual winners of the game. So let's follow the competition and we will see who wins. Good luck to all the players. So in today's competition, there are like a few changes from yesterday. There have been one new player. There is also 5 bots that have been updated. So in total, it's like 6 different changes. Hope you are having fun with this. At the end of the competition, there will be Anisse who speaking, who will wants to present the bot that he wrote. So thanks. So the final round for R2 Wars is over, and we can see that the results are pretty clear. There is like the same score for two of the players, which are basically the second and third, so we don't need to make another round for deciding who is second and first, because basically the first three players that win will be the ones that get the prize. I mean, there is no difference between the first, second, third. So we can see that the first one, the winner is Flacucho, which is an ARM 32-bit bot. The second one is Anisse, and the last one is Flagrod. So congratulations to all these three players, and well, I will introduce you now to Anisse, who will be presenting the code of the bot that he wrote.
Okay, can you hear me? Should be able to hear me now. I don't know if Pancake hears me. Okay, I hear my echo right now, so I'll close that. So my bots are all based on ARM32. These are all bots I sent. I'll make a quick tour of the three bots I sent. Even if there was 4 rounds, I didn't change my bot for the final round. So my strategy has always been to write as many bytes as possible. So my goal was to have a very high throughput. So I used this year I used STMIA, which is an ARM32 instruction. It can write at most 64 bytes, and it has write back, which means that the address register will have its content incremented by the number of bytes written. So it means that in one instruction, you can write and then modify your register, the address register, which is like mostly used for push or fast memcopy, for instance. So as I said, my goal is to have maximum throughput. I sent a first bot, which was pretty short. You can see it here. I will explain its content. So its main loop is 12 instructions. The main loop writes 512 bytes at once. It's a static bot, so it won't move. At the beginning, the bot is copied, it's loaded by LDMIA, and it's copied at address, which address 512. It overwrites itself and overwrites everything. So the main loop writes 512 bytes until the end of the arena. Then it jumps back here, and the address register is put back to 0 with this AND instruction, and it starts over. So it's the loop has 512 bytes every time from top to bottom. Yeah. So this bot, I don't remember the results. I think it was second as well for the first round. The second bot, it's a bit different. It's a bit more complex. My goal was to have a single loop that writes the whole arena. So I tried to have the main instruction write more bytes, because in the first one I only wrote 56 bytes. That's 12 registers. Yes, about 14 registers. This one I used a different strategy because the STMIA has even more registers, and it writes 60 bytes at once. So my goal, as I said, is to write the whole arena, and in the middle, I want to overwrite myself without dying. So the bot needs to overwrite itself without dying. It's also a bot that I can show you the code, but the code is the compressed version. It's the version I sent to Abel, and it's not the full the full version, because here what I'm loading in the register at the beginning, it's 13 bytes, and then I write them twice here and here, so the bot uncompress. It's effectively an uncompression. So it goes from 14 bytes to no, sorry, 14 instructions, 14 registers to 19 instructions, which is more than we can do in one instruction. So that's what this bot does. You can see it here, it does uncompress here, and then the reroute here. So the main structure is to write the whole arena, as I said. So it has a start address of I forgot 512 or something like that, and yeah. So the goal was to have the maximum throughput, and it has a bit longer setup because it needs it uses all the registers it can. So this has to be done in 2 instructions. The changing the base address and the instruction pointer, and that's it for this second bot. So it was quite good, I think. I think it should have been better than the first one, but we had many in the second round. We had many good bots being sent, in particular Flacuccio, which I think was better than this bot. And yeah, yes, one last trick this one uses. Since this bot is uncompressed, the branch here, it's a branch back 19 instructions. It can't be written with a label because I need to count the right number of instructions back. Because in memory, it won't look like this. It will look like this is the beginning, and then the rewrite, and then you have more instructions like this. Because in memory you have the 2 parts of 40 bytes each, about 40 bytes each. So the last one, which is the last bot now, which is the one in the final round. As I said, Flacuccio was really good. It used the same strategy as the same base instruction. I mean STMIA, but with a different strategy. And my goal was to have. At first, I explained a bit how it worked. I reverse engineered Flacuccio, and in order to understand how it was so good. And it uses the same STM instructions, but in the other direction. It uses the push, but it's basically the same. It's STM DB or decrement before. I don't remember, or DA. I don't remember which one exactly. It writes 64 instructions, 64 bytes. This is wrong. At once, so it writes all the registers possible. It makes heavy use of conditions for ARM 32 instructions. Almost all instructions have something called a condition, which is something we can see here. This is a move instruction, MOV, and then you can add like MI, for example, it means minus. It will check the condition flags, the flag registers, and it will execute the instruction or not. It's best if I show you Flacuccio's code. Flacuccio is here. This is, I don't know if it's the final version, but this is a version I reversed engineered from the second round. So maybe it changed in the third round or not, I don't know. But anyway, this is what I reverse engineered. As you can see, it's very simple and very clever. First, it checks, it gets its own address, and there's a pop. Here it's a compare instruction, and it will use this compare. This will set the flags. It checks if it will write below 320. This is 320, 0x140. And then if it's bigger, then it can write here 320 bytes, 64 by 5. And if it's not bigger, then these instructions will be not skipped, but not executed because they have the GE, which is great or equal. And then here you can see this is LE, so less or equal. If it's less than 320, it will move to the end of the arena, the stack pointer, and which is the address where the push will write. And then the next instruction, if it's yet another condition flag, this is a jump, because this is a jumping bot. It will jump where it wants. So this is a very simple yet very clever bot. So it will move if it's greater or equal, and then this is another move instruction. This is a jump back. Instead of encoding the branch like I did, this is a sub on PC, which is also very clever, which is start over without jumping, because if you're here, then it jumped to where it wrote, so it will jump to the beginning of the bot, but at another address. And here it's when the move didn't happen because it was not greater or equal, and then it will move back. And the rest is padding. It's mostly, this will be written in memory, the padding, and the padding is used to make other bot crash. And CC is very nice to crash x86 bot because it's debugging. I don't remember which one. I think it's debug or int. Yes, it's an int instruction. So, as I said, my bot was mainly made to beat Flacucho, and I think it succeeded in beating Flacucho in a few rounds, not all of them. It had a good win rate, but not 100%. And but the modifications are made, in particular, the start address made it weaker to other bots. So I made it's mostly the same as bot 2, except a few changes. First, I changed the start address because I noticed that Flacucho had the blind spot at the beginning, depending on the alignment where it started. It might not erase the below address, so the address at the start. So I decided to start the bot, the execution of the bot at 52. And I made all my instructions use condition as well, because I use the same architecture, so that's something I can do. In case there's a collision of the two bots, then one will start executing the instructions of the other. And if I have different condition flags, then it can't execute my instructions. And that's why I used MI. And I spent, in the setup, I spent one full instruction to do a CMP here that will make sure the flag of negative is always true. So which is why I use MI. And the last change, yes, this one also writes 64 bytes, unless the previous ones, which wrote only 60. I don't know why I did that. Maybe because I saw a warning when compiling that it shouldn't work, but it works with ASIL, so I guess that's okay. I don't know if it's a bug or not, but there's a warning if you check when you assemble this instruction. GNU assembler gives you a warning. I don't know why. And another modification is that in the padding bytes, instead of only having 0xCCC to crash x86 bots, I added SVC1, which is a syscall instruction, or it triggers an exception, and it makes the ARM32 bots crash. So that's it. As I said, it's a 19 instruction bot. in a single loop, it will write the whole arena. It's located at the beginning at address 52. That's where it uncompresses itself. Then it starts executing here, and that's it. I will now look at Telegram to see if any of you had any questions. Please wait a moment. No, I think that's okay. I think I explained everything. Yes, that's mostly it. So you can see it uses the same trick of uncompression. So this is not the code of the bot in memory. Huh? You need to remember that I have I load like 14 bytes plus then 2 of padding. No, yes, I load like, I don't remember. I need to count 1, 2, 3. I load a bit less. There are 12 instructions here and 2 padding, 4 bytes at the end. But when writing, it will uncompress in 2 instructions. This is where it rewrites itself. And I don't care about the value of PC or SP. SP, it will write PC at some addresses in memory. It will also write SP, which is R13, I think. I don't remember if it's R13 or 14. But yes. So that's it. It's that's about it. Yes. If you have any question, you can ask a question. Otherwise, I'm done.
Cool. Thank you, Anisse. It was a great explanation. We'll have another presentation about the bots from Cyanpencil after a short break. So thanks for participating. Thanks for winning, and congratulations for all your work. It's amazing.
Well, thanks for the organizers, and thanks a lot for organizing r2con. It was a great edition. Thank you.
You're welcome. Thanks. So sorry for the waiting, but seems like we have some technical issues. We'll try to fix them as soon as possible, and to not make the next talk start later, we will jump right now into the next presentation. So thanks for your patience.
Hi, everyone, and welcome to this talk called From Hardware to Zero Day. In this talk, we will be talking about how I started by buying a security camera and never actually use it for its regular purpose. So that's how it all started. And let's talk about first who I am. So my name is Pietro Oliva. You can find me on Twitter. My handle is Center. And currently, I'm a security researcher for R3. And in the previous roles, I was working with Sony, JP Morgan, NCC Group, PwC, and GMV in all different variety of security roles. And before we start, I just want to mention that none of this research has anything to do with my current or previous employers. So it's something that I did out of my own interest and free time. So let's go with the agenda. Why perform a security research on a security camera in the first place, right? And after explaining that briefly, we'll go through the previous research on previous work on this camera that I bought, and the challenge that I faced myself with, and the steps that I took to get to the end of this challenge. And then we will talk about the lessons learned and future work and conclusions. So what did we learn from this experience? And then you can have time for any questions you may have. So let's answer the first question. Why would you ever perform security research on a camera? My interest started because everybody says just IoT devices are not secure, just kind of by default without even, I don't know, personally verifying these things. And I wanted to do that. I wanted to have some personal experience where I could see with my own eyes what the security of these devices looks like. On that, I was looking for a challenge for myself and a learning opportunity. And this is where it all started. So this is the previous work that I found on the camera that I decided to target. And basically what I did, I just bought this camera, and the first thing I did was to look up the camera on Google and to see if there was any public vulnerability available. And the first thing that I found was that someone at IOActive disclosed some command injection vulnerability in the same camera and the next model. And unfortunately, this was already patched in the later firmware versions. And then I asked myself, is there really only one vulnerability for this camera? Because I couldn't find anything else. So here is when the challenge starts, and the challenge that I put myself into, which was hack the latest and greatest firmware update. So the way I wanted to do it was to make sure that I would learn something out of it. So I started from the hardware analysis and dumping the flash. So I could learn about the skills, how it would dump the firmware out of a chip instead of just downloading it from a website, maybe, or doing some black box testing. And I decided deliberately to exclude fuzzing or black box testing because I wanted to get familiar with MIPS assembly. And also I wanted to use a tool that I would be able to use on a train or on a plane or anywhere else. And that tool would have to be free and open source. And that tool, I found it, and it's called Radar2. So this is when what I did when I started. I just took pictures of the main board with my mobile phone. And as you can see, I could identify the main components. I mean, the pictures are pretty small in this slide, but by zooming in, I was able to identify all the components. And as you can see here, I could identify some flash memories and the CPU, the camera processor, voltage regulator, and so on. So one other interesting thing that you can do, because maybe, I don't know, for example, the CPU, you can see that it's under this metal shield. If you see the picture on the right, you can see that this shield has kind of been removed. And this is because this picture, I didn't take it myself, but I took it from the FCC website. So you may know that electronic devices need to pass some FCC certification. So they need to provide some details about the workings of the devices to comply with the regulations. So part of this information is internal features of the device. And if you're lucky enough, you might find some detailed features like this, where you can even see MediaTek, you can even know the exact CPU model without even having to try to open the metal shield. So after analyzing this board, I figured out that there was this 64 megabit SPI flash, and that's where the main firmware was. So I went ahead and tried to dump it. In order to dump it, I used a tool called Bus Pirate. And this Bus Pirate acts as a proxy between you and the SPI flash. In this case, could be even I2C because it's supported. So the way it works is it exposes a serial port for you and via USB, and then you can just issue commands that will get relayed to your I2C or SPI flash. But this process could be tedious if you do it manually. So you need some help from some other tool if you want to be quick in doing this operation. So I used FlashROM, which is a tool that can just do that and supports Bus Pirate. So it's able to talk to this board, which is then able to talk to the SPI flash. And we figured out that the 8 megabyte flash contained a main firmware. And this was actually kind of interesting because it took like about 15 minutes, and I initially thought it was just stuck. So if you ever have this sort of problem that looks like it's stuck, maybe it's just low, or just something to keep in mind if you try to reproduce any of these steps. So once I went ahead and dumped the firmware, I had this binary file, and I needed some way to analyze it, right? So the tools that I chose, but you could use others for sure, is Beanwolf for firmware extraction and Jefferson. Jefferson is the tool that Beanwolf uses to extract the GFFs to her system. And Radar is the reverse engineering tool. And I took the IP camera binary because it's the most interesting one, since it's the one that handles all the FCGI requests from the web UI. So that's where most of the vulnerabilities are likely going to be. Now, let's start talking about vulnerabilities. This is the first one that I found. As you can see here, this is the method that handles the login request. So you can see there is argument user and password passed to this match password method. Now, if the authentication is failed, it just keeps the entire code and returns an error. Fine, but if we go ahead, we will see that there is this HTTP getenv with this user agent being passed as a parameter. And that means it's trying to get the user agent string. And then after that, you will see that it's calling str with a string, with a pointer to this Firefox string. That means it's checking if the user agent is Firefox, and then it will check also for other browsers. Now, what's interesting about this is that there is nowhere any check whether this user agent string actually ever existed, if it was ever provided by the HTTP request. So this means that if you just send a request without an user agent header, this will just crash the IP camera process. Now, crashing the IP camera process means that you can basically no longer use the web UI at all, because it's the main binary that handles everything. So this was the first one. And now we'll discuss about the pain of the responsible disclosure process, because when I started reporting this, the vendor will come back to me and say, well, the camera is not supported anymore, it's too old, or something like that. And this was in December. And of course, it was in the middle of Christmas and Chinese New Year, coronavirus in China, and all these things. So yes, there was a bit of delay there. And then I was kind of abandoning this, but then I said, let's see if other cameras are affected. So if I can demonstrate that other cameras are actually affected by the same issue, maybe I can convince the vendor to fix it. So that's exactly what I did. And on the 24th of February, I warned the vendor and said, all the cameras, all the NC series cameras are affected by the same issue. And after the vendor kept ignoring my warnings, I decided to drop this as a 0 day, so they would act a bit quicker. And in fact, it did work. After that, exactly after 1 week, roughly, this vulnerability got fixed. And since then, all the next reports were handled way more seriously. And because they will know that if I set a deadline, that I will respect it, and I will publish a 0 day if we didn't fix the issues. And after I reported a few vulnerabilities, then they said, look, we published 2 firmware updates in the past 2 months. Please, can you promise you won't report any more things? And that's exactly what I did. So let's go ahead. Another issue is this wonderful Stack Overflow. So the way it works is there is a delete user method, and there is a wrapper around this method that is called delete multi-user, which does exactly what it says, deletes multiple users. Now, if we quickly look at this code, we can see that there is this delete user, and depending on the result of this method, it will set an error code via this sprintf method. And then we will see that there are some stack pointers being passed to some strcat. And we can see also that it's the same, one of the pointers is the same as the sprintf one. So we can assume that for every single user deletion, there is an error code that gets concatenated into a stack buffer. Now, every time we see a concatenation of things in a stack buffer, and we see that is not controlled anywhere, and there is a loop that is basically controlled by us because it depends on the number of commas, which means the number of usernames that we have. This basically means that it will overflow a stack buffer and it will crash the camera. Now, this could have been way more exciting than it is, but unfortunately, the error code is not fully controlled by us. I mean, the error code is a static string, except for the error code. So we could partially control the string by deleting certain users. For example, if we delete your own user or try to delete the user that doesn't exist and things like that. But this is not something that will likely lead you to arbitrary code execution. And by the way, this is what the POC looks like. It's just a bunch of commas, and it's enough to crash again the IP camera process. So you cannot basically do anything through the web interface anymore. Now, let's talk about next bug. This one is probably one of the most interesting bugs because it looks so simple, but at the same time, it isn't. So we can see very quickly there is this desencrypt method. We all know what this does, and we know it's doing some encryption. And we see that there are 3 parameters being passed here. One is the p backup, which stands for plain backup, TP-link, which is likely an encryption key, and then e backup, which is the encrypted backup. So all it's doing is taking a backup file, which is the backup of the configuration you can take from the web interface, and it encrypts it, because when you go from the web interface and make a backup, you don't want to expose all the secrets of these configurations, but you want to be able to, at the same time, re-upload them and restore them, but only the camera should be able to see these files, right? Now, the problem is that with this TP-link string being accorded here, this means that every single camera of the same model has the same encryption key. So this no longer stands. And now this is where the things get interesting, because we know the algorithm, and we know it's des ECB because of the patterns that you can see in the encrypted file. And interestingly, if I search some functional names, I could find a tool on GitHub that could perfectly decrypt this backup file. But if I tried with any standard DES implementation, I couldn't. I would just get random data. And I kept trying this, and I think I tried every possible implementation out there, Python, Ruby, or anything, and nothing really worked. And I thought I was really doing something wrong until I realized that one does not simply use an encryption key, because here's what happened. I looked at this code. This is the random tool on the internet I found called from some guy called Vico and me. And I don't know if it's themselves or code they took from here, I have no idea. And we can see a comparison of these are initial permutation table for the DES algorithm. And this was the only thing that they hadn't checked until that moment. The implementation looked exactly standard. And if we look closely at these numbers, we can see that they are exactly the same, except they are being decreased by 1 unit in every single number. And this is not only the initial permutation table, but every single constant in the DES algorithm was changed. So this solved the mystery, and I was able to then understand what was happening. So this must have been what happened in the mind of the developers. They had the option to use a strong encryption algorithm, but they decided to use a custom version of a weak algorithm. Now, we have this understanding, and we are able to analyze these files finally, and realize there is a small header composed of a magic, file size MD5. There is a fingerprint string that is a constant, and then some padding. After this small header, we are going to have the file entries. Every file entry is composed of the absolute offset from the beginning of the file with the file content. Then the file size, then some padding, and then the null terminated file name, plus, again, some padding. So now that we have this understanding of the file format, this becomes very interesting, because what we have here is we are providing file names and file contents, which gives us potentially arbitrary file write on the file system. So let's go ahead and see if this is actually true. Need to fire up my VM. All right. So let me share. All right, here we go. Hopefully you can see my screen. So here we can see a very simple script. I called it 1.sh because it's for demo 1. So we have this create config. It's creating, it's forging this configuration file with these parameters. So we are just going to upload 2 HTML files, demo 1 and demo 2. And then we're going to encrypt them with the NC200 encryption key, which is TP-Link. Now, if you run the script, it should have generated a file that I should be able to upload to the web camera. Let's check if it's going to work. So we have management, browse, all demos, CFG, restore. Now, this is the moment where my camera will reboot, and hopefully will come back to life. It's rebooting because it could be overwriting some critical files that needs more services to be restarted. So that's why it's actually rebooting. But for our modification, it wouldn't be necessary, but that's not what this feature has been intended to do. So it's understandable. Let's see. It's coming back to us. Yes, we can see some things. Okay, here we go. The camera is back. So let's go for demo 1. Oh, wait a minute. Demo 1. Of course, there's a network problem. Yes. So as we can see here, what I did was replacing the camera frame with this wonderful and very useful tool called Doom. So it is not very useful by itself, but it's just to prove that we can basically customize our camera and do whatever we like with it. So this is not very useful by itself, and then this is when it becomes the second demo. So as you have noticed here, there is this thing called the TP-Link camera plugin is required, because supposedly you should install the plugin to view your camera. Now, if all this is totally wrong because it's 2020 and we cannot accept this anymore. That's why I made this demo to HTML. So as you can see, we can not only customize the camera with useless features, but also improve our cameras. So we can not only compromise other people's camera, but we can actually do some useful things. So now I'll go back to the slides and continue with the presentation. All right, hopefully you can see my screen again. So this is a better vulnerability that I found compared to the Stack Overflow and the null pointer. This is a command injection. This is more exciting now because it gives us arbitrary command execution as root. How does it work? The way it works is there is a CGI that accepts an encryption key for some reason. And what it does is it's echoing this encryption key that you control in some file in TMP. And you can see that it's being sent in this CM command method, which is just a wrapper to system, basically. So it gives us arbitrary code execution as root. Now, the downside of this is that it only works on NC260 and NC450 cameras. But the coolest thing about this is that if you notice, this is a screenshot taken from a mobile phone. So I'm sorry for these circles being not very pretty, but I really wanted to show that I made most of this research on the go. So in this case, you can see it was in flight mode. I was literally on a flight to Egypt when I was doing this. And I was massively bored. I didn't know what to do. And that's what I did. And it was great. But now we got this, and we can execute command as root. Great, but we want more because it only affects 2 cameras. That's when this wonderful bug appeared. As we can see here, there is again this CM command method, which is a wrapper to system, and right before that there is this MDNS responder POSIX, which is the bonjour daemon. As you can see, it's getting started with this parameter -n%s, and if we trace back the parameter, which is this v0, it comes from this frame pointer from this stack buffer. And the stack buffer comes from here. It's populated by this bonjour get name. That means if we can control the bonjour name of the device, we can get arbitrary command execution. And after I checked, there was a wonderful method called set product alias check, which means this is what gets called when you try to execute this set sysname.cgi. Now, the thing with this is that this URL was completely blind if you were trying to find this URL via black box testing or anything. It was not exposed from the web interface. As we can see here, you can look at all the code, but I can tell you from the beginning that the only real check here is this strlen, and it's checking if the length is greater or equal than this 0x81. So as long as it's less than that, the name will be accepted and it will be written as a bonjour name. And this is what I think was going on in the developer's mind when they wrote this. And basically, this gives us an easy root shell on 7 different cameras. So this is what I call a bug to rule them all. Now there is a slight difference between the models, which is all of them except from NC210 can get this triggered via this set sysname. But the NC210 actually does some validation except from the length check. So we need to figure out another way to use it. So let's go for the demo and see what happens. All right, hopefully you can see my screen. Let's go for demo 2. Now, demo 2. This is how we exploit the command injection on this special camera, NC210. All we are doing is basically combining these two vulnerabilities, the hard-coded encryption key, so arbitrary file write. So in this way, we can write this system.com file where the command injection is stored, the bonjour name. So what we are doing is a trick. So instead of setting it through the CGI, we are going to upload a config file, a backup file, and we are going to add a payload that we generated with Metasploit, just standard reverse shell. And we are going to encrypt it with its own key, NC210, which is slightly different, I think, from the NC200. And then we just start our handler. Now, if you execute this, it should create the files that we need. And now it's going to start the Metasploit framework. And now we will go, here we can see that the camera is already running. It's in QEMU because I don't physically have this camera. Now let's see what happens if we upload this file. Hopefully it will work. Sorry, again, this might be slow because it's QEMU. So not a physical device. Yeah, here we go. So management, browse, demos 2, systemconf.cfg. Now this will be rebooting again. As we can see, it's doing some weird stuff. That's because you can see a lot of errors going on. And that's because, of course, it's not a real device. So there are actually so many errors. And I think it's a miracle that it still works. And I actually had to make some small patches to these binaries to make them work. Specifically for this bonjour stuff, because there was some error when starting the bonjour daemon, but was totally unrelated with our vulnerability. It could not get the IP address of the camera or something like that. And that's because it doesn't even really have a real network interface. It's supposed to have Wi-Fi and stuff, but it doesn't have any of that. So hopefully this will not take too long. But in the meantime, we can go ahead with the next demo, I think. Yes, it's going to take a while. Okay, let's go for the second demo. So what we have here is we are just using this Metasploit module. This Metasploit module is using the vanilla version of this exploit, which is using this set system name to basically get a reverse shell. Now we'll try on both this NC450 and NC200 cameras. Okay, so what they're doing is just making this request, injecting the command, and downloading a payload from us. So let's see what happens. And the same for NC200. And by the way, this Metasploit module I made supports all the 6 cameras that can be exploited using this method. So we can see that it managed to log in. This is the NC450, and it's running QEMU, while the NC200 is the physical one that I have. So it should be a bit faster. Okay, fine. I can run them at the same time because the port is busy. So let's wait for the first one to finish. Hopefully the other one rebooted. Yes. So we log in now. It's supposedly starting automatically, but I made a small script because it's not a real device. It's just starting the LightTPD daemon. So this is starting the everything. And now we should see here that we have an interactive reverse shell on NC210. And we can see here this MDNS responder POSIX, and here is the command injection that we have. Now, hopefully this progressed. Yes, now we have a shell on the NC450. Yes, here we go. As you can see, everything is run as root, of course, so you can enjoy full control here. Now let's try the same thing for the NC200, which should be quicker. And it should work now because it's not, the port is not busy anymore. Yes, here we go. There you go. All right, so that was the demo. I will go back to the presentation. Hopefully you can see the screen back. So what did we learn from this experience? The first thing, check the vendor website before dumping the flash because it might be easier for you. So I didn't do that deliberately because I wanted to learn how to do it. But please, 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 if you ever encounter a device and you want to hack it, please go to the website first if you are not really interested into that and just want to analyze the firmware. The second point I wanted to make is that these cameras were all vulnerable to the same thing because they shared a lot of the same code. So the same code equals same vulnerabilities. So don't discard that when you find a vulnerability that will not affect other devices. And the third point that I wanted to make is dropping a 0-day is not necessarily a bad thing. So in this case, it helped a lot because they started taking my reports more seriously and they started fixing stuff. And another point that I wanted to make is that reverse engineering can reveal bugs that you can never or very unlikely find using fuzzing. Like this setsys name was not exposed at all. So it will be very unlikely or virtually impossible for you to find that out and the correct parameters to trigger the vulnerability. Now, future work, I promise myself that I will not report anything to TP-Link regarding these cameras, that I will move on with my life. So if you want to do any future work on this, you can look at maybe things that can be exploited from the cloud. I didn't personally because I wouldn't trust my camera to connect to the cloud. And same applies for the browser plugin. You could maybe find vulnerabilities there and make your browser vulnerable thanks to the plugin. Or look for baseband. Since it has Wi-Fi, maybe you can find some, I don't know, security issues that can be exploited within the Wi-Fi range without even having to log in into the web UI or basically zero-click attacks. Now, conclusions. I think we proved that there was indeed more than one vulnerability on these cameras. I think the researcher that looked into the previous camera was just happy with his root shell, and he probably was not dedicated to doing this in his company. So he found this issue and he reported it, and that's where he stopped. And another thing that I want to say is that you don't need any expensive tools to find this issue. The bus pirate is really inexpensive, maybe $30 or something. And radar is free to use. So you can do this, and you can do this even on a plane when you're flying, or on a tablet, or anywhere you want. And another point that I already made is don't just think that fuzzing and black box testing is going to solve all your problems. Reverse engineering and code review is really, really helpful in finding the issues that just cannot be identified by these means. And of course, it was a good idea to never connect my camera to the cloud. I don't invite you to do it unless you really want to research this insecurity, which is a good idea for a new talk. And I can say now, from my experience, that these devices are indeed insecure, at least the one that I looked at. And now another very important point, and it will be my closing point, is that we, security researchers, with vendors have a shared responsibility at making things more secure. because if I didn't find these issues and I didn't press them to fix them, nothing would have ever changed. And if they, if they in the future make devices like this, they will remember some guy is going to annoy us until we fix everything. So they will get better and do better things. And everybody gains from that. So that was all, and thank you for listening. Have you got any questions? Okay, so here's the first question I got. Do you need a bus pirate? So this is the tool that I chose. You can probably find equivalent. You just need anything that talks the SPI protocol, and that works for you. If you don't want to do this, you don't have to. You can download for some cameras still the firmware from the website. So if you don't have the equipment, which is just one board, you can just download the firmware if you want to get started. I hope that answered the question. The next question I got is, did you run radar on the camera itself yet? This is a funny one. I didn't, and it wouldn't be super useful, I guess. But it's definitely something that you can do. I managed to actually compile radar on my mobile phone. So I guess you could do the same, but it will probably be, I don't know, you will have to probably cross-compile it because I don't think you will have enough memory on this cameras, at least the model that I have. Did you try the compiled MIPS code in Ghidra decompiler? If yes, was it correct? So I did use Ghidra decompiler in my life, and I have to say that I think in general it's correct. And in fact, I think that sometimes even compared to IDA, there are scenarios where Ghidra is more reliable than IDA at decompiling things. And it's also true the opposite, where you can have IDA decompiler being more precise than Ghidra. But in general, Ghidra is a very good tool for MIPS, and you can also use it in radar, by the way, which is something that I also did, but not for this project specifically. Because as I said from the beginning, I wanted to learn MIPS code. I wanted to be able to learn to read MIPS code. So I hope that answered your question. The camera binary has no compiler protection. Stack cookies, not executable stack randomizing. Probably most of these things are disabled. I'm sure I haven't seen any stack cookies anywhere, and I think non-executable stack is also disabled, and I think also ESLR is not there. So if you want to really exploit these things, I think you will have a lot of fun, but you need a bug first. So, and that's not the buffer overflow that I found, because it's very tedious to do it. Is the drop.bond, the fixed one, available on your Twitter? Possibly, yes. It's on full disclosure, it's everywhere. It's not super exciting from an exploitation point of view, but you can definitely see the details on full disclosure. And on my Twitter, I'm sure I share that one. Now, the next one is exploitation from TP-Link Cloud doable with the same approaches? Is the vendor aware about these possibilities? So the answer is, I don't know. I deliberately never connected to the cloud because I didn't want to connect my camera and expose myself to any unnecessary risk. But there is a chance that you will be able to trigger some of these things. But if your firmware is updated, then you should be okay unless they exposed other things in places that I haven't looked at. Keep in mind that this is a personal project and is not at all intended to be a comprehensive security research on this camera. I'm sure you can find even more. The next one, how do you have the symbols in the assembly? That's a very good question. So apart from the NC210, for some reason, all the camera firmwares have the function names just available. They don't have full symbols, so you don't have like variable names. So the variable names that you see in there, I put them myself with the radar. But the function names were there, except for the NC210, which is a bit of a special camera because it is also the only one that has an ARM architecture instead of MIPS. So yes, so this is how I have the symbols. For the NC210, I didn't have them at all, but you can use the other cameras firmware to compare methods, and also you can help yourself with the strings. It's not that hard. The code is relatively simple, I think. Now, the next question. The firmware on the website was not encrypted. Yes, exactly. The firmware is not encrypted. Everyone can download and analyze it. So if you want to do it, then you are free to do so, and it's going to be easy for you to look at it. So I think that will be it. I don't see any other questions. So I will terminate here if there is no further questions.
Thanks, Pietro. It was an amazing presentation.
Thank you.
So yeah, hope that you also had fun presenting. We'll jump into a short break, and then we will introduce the next presentation. So thanks. So after this short break, I will be playing the video from the Cyan presentation. This is the bot from r2con2020 competition that took the 3rd position. So hope you enjoyed. And after this, we will jump into the next presentation, the Symbolic execution in R2.
Everyone, hi, I'm Cyanpencil and I'm here to present my second place along with Anisse, and yeah, so this bot is really simple. I will explain exactly how it works. So it's r2con2020, and I'll explain why it works. So this is the initial setup, nothing special here. I just load my position here. I just set up some initial registers. Here I load my main payload, which is this one. So those are 7 instructions and they fit in 4 registers. X1, X2, X8, X9. Those contain my code. And then next step, I write myself in a known position here and I just jump there. So this is nothing special. So this is my main loop. It's only 3 instructions. It's pretty cool. Why is only 3 instructions? Thanks to this test bit 0 instruction here. So what I'm doing here, I'm just writing myself over and over, going through lower addresses, right? So this store per instructions lets me do a really cool thing that is post incrementing. So the value of x3 gets changes after the values have been written to memory. And while this is only for adjustments, this minus 0x38 is what really makes me go backwards a lot. And after I wrote myself, what I do is I need to check if I went below 0, right? And this instruction is what lets me do it. This is test bit 0 on x3, and I check if bit number 30 is 1 or 0. And if it is 1, I jump 12 bytes backwards. That's what I do. And this instruction is really cool because it lets me do basically a branch and a jump at the same time, and you don't have this in x86. Also the branch is PC relative, so this is super cool because I don't need another register to keep track of where am I. I just use my program counter. So what is my strategy? To explain my strategy, I'll show you a quick simulation of a run between me and a competitor from last year. So I noticed that most of the x86 ones use the instructions to push a lot of stuff on the stack, right? But the problem with that is that if you push a lot of stuff on the stack, the direction you're writing is always defined, right? So you're writing from high addresses through lower addresses. That's what you do. You're really quick in writing, but like all writes are sequential and are really predictable. So what I did is a bot that escapes from writes that are too fast to fight, and I escaped to lower addresses. I'll show you a mock run. Yeah, here we go. And as you can see, my bot goes backwards and loops over at the end and lets me win against basically anyone that uses this kind of trick to write a lot of stuff, right? So I lost against people that had ARM or that had really unpredictable ways of writing stuff. Yeah, so this is the part where I check that I loop over. I just add a very big constant and I basically end up on the high addresses once again, and I just continue. So my main vulnerability that lost me 2 matches is that I was not able to write on the first row, and I didn't really have too much time to fix it because I decided to join just yesterday. So yeah, maybe with more time it can be improved. But yeah, it was an amazing competition. I had so much fun. I thank you, Scooter and Pancake, the organizers. It has been amazing, and I really look forward for next year. I will definitely join again with an improved bot, with more time. And yeah, that's it. So thank you very much, guys.
Hello everyone, I hope you're enjoying r2con 2020. Today I'm going to be covering a plugin I wrote to integrate r2 and Anger. This talk is pre-recorded, so feel free to ask any questions you have in the chat during the stream, and I should be available to answer them. So as we all know, r2 is a Unix-like reverse engineering framework, and Anger is a binary analysis framework developed at UC Santa Barbara and Arizona State University. Anger has many features, including IR lifting, program instrumentation, symbolic execution, control flow analysis, value set analysis, etc. And my plugin is a start to integrating some of these features with r2, though most of my focus was on the symbolic execution engine. Just as a quick refresher, symbolic execution is a way of determining what input values are required to reach certain program states. So normally when a program is executed, we'll provide it with concrete values that, amongst other things, determine which parts and in what order the program executes. With symbolic execution engines like Anger's, an interpreter follows the program, providing symbolic values for program input and computing the constraints for these symbolic parameters along each execution path. So in specifically the Anger implementation, the program is listed to VexIR, and the program is interpreted by what they call the simulation manager, using what they call bit vectors as symbolic values, adding constraints to these symbolic values, which can eventually be passed to the Z3 constraint solver. Each path in the execution has an associated state, and at any point in the exploration, each state is in a stash or group of states, normally the active, dead-ended, found, or unconstrained stashes. So now I'm going to show an example on a simple keygen. So if we run this challenge, we can see it prompts us for a password, and then there's a success fail check, and in this case, we entered the incorrect password. So we can open this in Raider 2, and if we seek to the main function, we can see the fgetS that gets our user input. Then there's a call to this function, which does a check. And then we have our success and failure branches based on the return value of that function. Now, normally we would just reverse this function, which is pretty small, so it shouldn't be too difficult. And the additional integration of the Ghidra decompiler makes it even easier. But we're lazy, and so we're going to use symbolic execution to solve this automatically. So all modality commands are prefaced with the capital letter M. So we're going to start by initializing modality and exploring to the main function. So we can see that this exploration succeeded, and the state is highlighted in blue. In addition to the highlight, all current active states are commented with their number, and we can see that this is state number 2. Now, this is somewhat unexpected, as we wouldn't think that there'd be any state splitting between the entry and main functions, especially on a Linux binary. And so to investigate this, we're going to list the states, and then we're going to seek to state 0. Now, from this ptrace call, we can infer that the purpose of this function is to check for a debugger, redirecting execution to this infinite loop if one is detected. And the Anger state splits whenever ptrace is called, which is why we have several states active. So we're not interested in the states where a debugger was detected, so we're going to kill them and then return to the main function. And we can see that our active state index is now 0. So to finish solving this challenge, we're going to explore to the success branch. And then we're going to kill all states except for the one that we're interested in using the MSE command for extract. And we'll extract state number 4. And then we can see that the state we're interested in is now index 0, and then we have all these dead-ended states. So now all we need to do is dump standard in for our state to get what the password should be. And we can see this right here should be our password. So we'll copy that. Paste it, and that appears to be the correct password. Now, I went through this challenge rather slowly, but in an actual CTF, for example, we could solve it in a few seconds. Just to show you, I'll open it in R2 again. I'll use a different exploration technique this time. I'll explore until the string nice is in standard out. And then I'll extract state 4 and then get our input. And we've solved it rather quickly. Now we're going to solve a different challenge to demonstrate yet another exploration technique. So we can, once again, run this binary. We can see it expects user input, and then there's a success failed check, and in this case we entered the incorrect password. So once again, we're going to open this in R2 and run some analysis. Now I can tell you ahead of time that the graph view in this main function is too large and complex to render in a reasonable amount of time. So I'm just going to stick to the linear disassembly. So I'm actually going to disassemble the first 1000 instructions and print that. And we can see in here there are a whole lot of calls to these two functions, maybe good and avoid me. So for anyone who has used Anger before, a common technique is to pass to the explore function a list of addresses for Anger to find or avoid during exploration. So similarly in modality, we can mark places with find and avoid comments. So if we list our functions, we'll try first seeking to the avoid me function. And we're just going to add a comment there that says avoid. And then we can seek to the maybe good function. And if we look at the graph view, we can see that the success branch after our compare is over here. So we're going to add a comment there that says find. So now all we need to do is run the explore command, me. And modality will compile these find and avoid comments and call the explore function for us. So it looks like we found a solution relatively quickly, despite the complex control flow of the main function. So we can see that here, this is active state 1. I'm just going to extract that to kill whatever extraneous state there is. And then all we need to do is get user input. And we have our password. So we can just quickly test that. And it looks like we had the correct password. So one general difficulty with writing Anger scripts is that it can be difficult to tell what the backend is doing during exploration. So modality provides a number of useful hooks to help visualize the backend. So to demonstrate this, we'll start by opening the r200 binary. All our hook commands are prefaced with mh. And so for the moment, we're just going to hook all functions. Next, we'll explore to the main function. And we can see here in our output our additional entry function calls. And this call to pre-trace, which is once again used for anti-debugging. So since this binary has the same anti-debugging trick as the previous one, we'll extract state number 2. So next I'm going to demonstrate the loop hook. And so we'll run the command, and we see that our analysis detected 7 loops. And then we'll explore to this basic block on the right. So we can see in our output that some debugging information is printed each iteration. And this compare instruction is helpfully printed so that we can see this counter increment each time. And then also the malloc call is printed. So tracing is generally useful, but the main purpose of the loop hook is to ease with identifying path explosion points. So to illustrate this, we're going to explore to the end of the loop in this function. And we'll see our number of states rapidly grow. So we're getting a lot of output, and we can see that the number of active states is rapidly growing, 89, 144, 232. So obviously we're encountering path explosion. To solve this, we need to add merge points, but in the interest of time, I'm not going to demonstrate that today. So path explosion is a difficult problem generally, and I don't have solutions for that issue today, but these hooks should hopefully be helpful for people in identifying problematic code blocks. So I also have a few notes on state initialization. So in the previous examples, I just allowed modality to automatically initialize some state at the entry point before exploration. But this is something that the user has more fine-grained control over. So if I just open this challenge, show the help related to initialization. So with MIE command, I can initialize at the entry point, just like modality normally would automatically. I also have the option to initialize a blank state, which is basically just a empty Anger state at some location. So there's a blank state. But more interestingly, I can initialize a state from the current debugger state. So if I start the debugger, continue until the entry point, and then if let's go forward a few steps, and then initialize from our debugger state. See, now we have a Anger state where it attempts to copy as much information from debugger memory as possible, and then initialize a state at that location. So now we're going to move to the next section, which will cover vulnerability discovery and exploit generation. Now, there's been plenty of previous work in using symbolic execution in automatic exploitation tools. See the DARPA Cyber Grand Challenge for examples. But there's normally been a wide gap between the manual exploitation process and fully autonomous tools. So modality is an example of a hybrid approach where much of the tedious and repetitive work is handled by symbolic execution and other scripts, while, for example, the higher level approach to vulnerability discovery is handled by the reverse engineer. This interactive approach is the best of both worlds, I think, given the current state of the relevant technology. Okay, so first I'll give a high-level overview of my current exploit generation implementation, and then I'll show how to use it on several toy binaries. To be clear, my implementation at this point is somewhat rudimentary, so for many reasons, you're not going to be able to run this on Google Chrome and expect anything useful back. But it's a start toward more sophisticated tools. So the first step of vulnerability discovery is a relatively standard exploration of all paths from the current simulation manager states. During exploration, it looks for states with unconstrained program counters. And when one is discovered, it attempts to constrain that program counter to an arbitrary value. If this is successful, we'll assume this is an exploitable state. So it then iterates through our symbolic buffers like standard in, checking which bytes are unconstrained and which ones need determinate values. And the result buffers form our base shellcode. The final step is to generate a payload based on our base shellcode. And this will include generating any ROP chains, bypassing additional protections, etc. And the result of this is written to a file and output on the terminal. So first I'm going to demonstrate how this works on the following basic exploitation challenge. As you can see from the source, it reads user data from standard in into a 20-character buffer using scanf, which can obviously lead to a buffer overflow. So next we'll open this binary with R2 and we'll load modality and list the help. As you can see, the exploitation functionality is under the ME command, both letters capitalized. So we'll run that to see what it comes up with. So after a few seconds, we can see it finds an unconstrained state. and then it constrains the program counter and loops through the standard in bytes, checking which ones are constrainable. So we'll ignore most of the terminal output for now, just looking at the base shell-coded outputs. We can see that the part of the shellcode that overwrites RIP is colored red. So now this example is somewhat interesting, but it's not really something you need symbolic execution for. This base shellcode could be generated much faster just by fuzzing and pattern matching. So next I'm going to show a variation on this toy binary where symbolic execution has an advantage. As many of you have no doubt experienced when writing exploits, oftentimes when attempting to get control of RIP, your buffer overwrites some earlier piece of data on the stack that is essential to program execution reaching the return instruction. So in these situations, you often have to spend 30 minutes in your debugger, altering your shellcode to maintain the original stack values to prevent the program from crashing. So symbolic execution, as we will see, can automate or at least simplify this process. So we'll take a look at this challenge, which is just the previous one, but with a slight alteration. If we look at the vuln function, you can see there's a couple comparisons with values on the stack, and the program will exit if any of these values are not what they're expected to be. So we'll just run the me command once again. It's constraining the standard in bytes. And you can see here there's this skipped number, which is larger than before because there's a certain number of bytes that could not be constrained to an arbitrary value. So if we look here at our base shellcode, it's a little bit different. You can see that there's this byte here, and then these set of bytes, and these are the local variables for which there was a check that would exit the program if their values had been altered. So this is a simple example, but symbolic execution can solve for pretty complex shellcodes using this technique. So as we all know, binary exploitation has been significantly complicated by the introduction of protections like ASLR, DEP, etc. So Modality attempts to use, amongst other things, R2's built-in ROP search to generate shellcodes that bypass some of these protections. So I'm going to spend the next segment of this presentation just going over a few of the protection bypasses that I've implemented. So the first one of these isn't really a bypass, but rather a trick for CTFs. So often exploitation challenges have functions built in for the exploit to jump to. So Modality will attempt to detect any win functions and will dump shellcode that jumps to it. So I'll just show an example on this binary. We can see two function calls from the main function. One has our buffer overflow. And then there's this one, which has a call to system. So this is our win function. So we'll just show the exploit generation once again. Constraining standard in bytes. And then we can see here is our payload for the win function. It guesses based on the call to system that this could be a win function, so it dumps the shellcode, and then it also writes this to win.txt. So we'll just test that. So a common mistake with these shellcodes is to run your exploit like so. If you're running your exploit like this, standard in and standard out won't be redirected correctly, and so you get this segmentation fault. So just one trick is to use cat. And it looks like we have our shell. Okay, so our first real bypass is going to be a ret to libc. So I'll first give a quick explanation of how this works for anyone that doesn't already know, and then we'll see how modality generates these payloads. So for the moment, let's assume that we can overwrite a return address, but the stack is not executable, so we need a ROP chain. One common way to get a shell via a ROP chain is to return to a function like system in libc with the appropriate argument on the stack. So let's quickly just take a look at how to do this manually. On this 32-bit binary, I'll limit our search space. And then first, let's get the address of system. See, there it is. And then we can search for the bin sh string. And there it is at that offset. So if your system is 32-bit, as per the calling convention, you'll want both addresses on the stack so that when you return to system, it will pull the address of bin sh as the first argument. Now, if your system is 64-bit, remember that the argument needs to be passed in RDI instead. So I'll just show an example of that. And there's our address of system. Then we'll attempt to find our bin sh string. And there's at least one instance. Oh, and then also we'll want to find and there's our prop RDI. So we can use the addresses we found to pop the argument we want into the RDI register, and then we can return to the system call in libc, and it will use that string as its argument, hopefully giving us a shell. So just to show how modality will do this automatically, we'll run our exploit command. Constraining standard in. And then here, it attempts to generate our payloads. Okay, so we can see it wrote our payload to this ret to libc txt. So we'll test that. And we can see we have our shell. So next I'll explain and demonstrate the ret to plt payload. So ret to plt is a technique similar to ret to libc, except we return to addresses in the procedure linkage table rather than libc. So once again, I'll demonstrate how this works on our test binary. So if we list our sections, we can see we have a few here. And one of these is the procedure linkage table. So we'll seek to that. We can see here these stubs for our imported functions. And the one that modality attempts to use automatically is this call to system. And so if we jump here with the appropriate argument either on the stack or in the RDI register, depending on your calling convention, You essentially accomplish the same thing as ret to libc, except entirely within the binary. So I'll attempt to demonstrate this, running our exploit command. And here we have our payload. So I'll just test this quickly. Should be in the ret to plt txt file. Actually. And we once again have our shell. All right, so to recap what we've done so far, we have solved some reversing challenges with symbolic execution. We've shown various state initialization techniques, including from the R2 debugger. We have used Anger to explore for states where the program counter is unconstrained for the purposes of vulnerability discovery. We've used this to generate basic exploits. And we've shown a few ASLR and DEP bypasses, which are automated as part of our exploit generation process. So looking forward, I plan to use some of Anger's built-in analyses to augment the analyses built into Raider 2. I plan to integrate the Symbian exploration technique from Anger. So Symbian is a somewhat experimental way to switch between concrete and symbolic execution that's built into Anger. So my method is kind of the naive approach of just copying data from the debugger into the Anger state. Well, with this technique, Anger reads data from the debugger memory directly while doing emulation. Now, the latter technique should be much better in principle, but for a number of reasons, it wouldn't work immediately with the rest of my tool, though I do plan to make this switch eventually. So I could also start tracking heap usage. Now, unfortunately, Anger's heap does not function like any sane memory allocator, which may limit the kinds of analyses that can be reliably built on it. But in principle, it could be used to detect use after freeze, double freeze, etc. So there's also more ASLR DEP bypasses to explore. I only scratched the surface in my talk, and Anger can definitely be used to generate like longer and more sophisticated ROP chains. There's bug fixes / increasing the robustness of the tool, and also Windows integration, which should be possible but is so far untested. And that's all I have for you today.
Thank you, Chase. This was a great presentation. I guess that there is some questions from the attendees. So let's see what we have.
Yeah, so the executables used in the demos. So most of the binaries are from the Anger repository, and the Anger people got them from, at least the ones I used from Def Camp, one of their CTFs. For the exploitation challenges, it's been a while, but if I remember correctly, I grabbed some of them from the exploit exercises website. And I think I altered a few of them to make them a little more challenging for the Symbolic execution engine. But all the binaries I used, most of them were relatively simple, just because A, Anger is slow, and B, on the most complicated binaries, it can take Anger 30 minutes or an hour to explore to some state that you care about. So that's why I kind of used a lot of these like intro level CTF binaries.
Cool. There are more questions. Yeah. Do you think that it's possible to integrate the tools to find or exploit heap bugs?
Yeah, so there's some limitations imposed by anger on that. I answered this a little bit at the end after the question was asked, but the memory allocator in anger does not behave anything like glibc or any other memory allocator that you might be interested in analyzing. So any, like if you detect, for example, a use after free or something, the memory addresses that you might pull from the anger state aren't going to correspond to your addresses from the, like, during execution. So there may be some cases if you add to the anger heap simulator that you can get some useful analysis, but I think in general, something like BAP is going to be a better framework to look at heap issues.
Cool, thanks. More questions?
No, guys, this one was the last
This
one.
was the last one. Okay. Thank you, Chase. Thanks for attending the conference and speaking out and presenting your work. It was cool. We'll go into a break. And after this, we will continue with the next presentation. Thanks. So we're back to the next presentation. This is a presentation about the keys to homebrew. It's all yours.
Hey, so this talk is called The Keys to Homebrew. It's about running custom code on the BMW display key, which was a smart key released by BMW in 2015, used on the 5 Series, the 7 Series, and the i8. So in 2015, BMW released the touchscreen display key fob, which was an option starting in 2015, but the car was released in 2014, so this was like a year after the car is released. I'll go through who I am, what the product, what this talk is about, sort of like the motivation behind it and the process. So I'm Jeff. I'm an automotive and R2 enthusiast. I've been working with R2 for the past almost 7-8 years or something. And I drive a 2017 Subaru BRZ, which, despite being released at the same time as the i8, it's significantly less high-tech. It has a only gasoline engine, and this is the key. It's only got 4 buttons, no touchscreen. It's pretty uninteresting to play with. The only sort of interesting thing that you could do with it is maybe do a replay attack or something. There's the famous roll jam attack on all these RF keys, but that's been done. It's nothing that I want to keep doing. Like, the whole Subaru experience is pretty low tech. It's not a very fun platform to be spending your quarantine inside playing with. So the BMW i8, it has a lot of really more high-tech features. All of the used ones cost exactly $60,000. It doesn't really matter the condition that they're in. I don't have one, and I'm probably not going to buy one, but the key is the most interesting part of this car for me. It's got a embedded OS. They don't really describe anything about it. I think BMW doesn't really want to advertise anything about the key other than it's a BMW key. It has a touchscreen interface. It's pretty cool to see in a key because I've never seen something like this before. So a friend and I bought a batch of them from eBay. They were like $99 each, which for a car key is actually relatively cheap. But I think in order to get them programmed for your specific car, you need to go through BMW, and they charge quite a bit. It's the most high-tech car key I've ever seen. So I thought it was a fun challenge for a week or so. So the very first thing when the keys arrived, you start to tear them down basically immediately because I don't know any of the hardware that's in it. I've never seen one of these before. When you open it, you can see right there. There's the Freescale branded chip. So that's the main application processor. The shield on the left, that's where the RF module is. And up on the top on the right, you can see where there's a NOR flash chip. Checking with the datasheets, it has a NXP ARM9 CPU. It's a branded MCI MX285 AVM4B, and it's running an ARM9 CPU. The J at the end means it can run the Giselle instruction set, which is like a hardware ARM instruction set, which I've never seen one of these before. You can run Java natively. That's pretty interesting. It's got a 64 megabyte NOR flash chip on the SPI bus and 128 megabytes of MDDR RAM, which for a key, that's pretty unbelievable stuff. The CPU, it's running at 454 megahertz, and compared to today's mostly embedded stuff is like smartphones that have been repurposed. That doesn't really seem like very much, but comparing it to something that was like equally revolutionary to the key, like the key business has changed forever from this BMW key. Like the original iPhone back in 2007, another ARM CPU running at a slightly slower clock speed. So that was running at 412 megahertz, and this key is running at 454. They have the same amount of RAM, a similar display. So the key has a 320 by 200. The iPhone has 320 by 480. So it's relatively similar in hardware to the original iPhone. In terms of power, the iPhone has a few more interesting things like a camera and GSM and Bluetooth, but the key is about the same power as a smartphone from about 10 years ago. It's pretty interesting hardware there. BMW, of course, they didn't provide any firmware to get from their website, and I'm not familiar with the platform or anything. So the first thing to try to do was remove the flash chip, try to see what is going on. Everything on the board is a BGA. I'm not very good at soldering, so my friend was able to get the chip off with a hot air gun and solder up all of the magnet wire to the NOR flash chip, and we're able to dump it with flash ROM on the Raspberry Pi. Unsurprisingly, the key runs Linux, and U-boot, you can tell because it says a U image for the type of Linux kernel ARM bootloader. It has an extended 2 file system that contains all of like the main OS data, all the binaries, and a JFFS2 file system, which is used for logs most likely. It seems like a pretty generic embedded system from this point. When you mount the ext2 file system and poke around, it has like a bunch of sort of like sprites that get loaded by the keys UI. It has some like really over-engineered key type things where it will check if it's overheating and tell you that you need to cool down your key. Various things like this. It seems like way overly complicated for what a key should do. So with the file system extracted, I built a kernel and then took the root FS and tries to run the whole key and the full system emulator of QEMU. It has this binary BMW MKD, which the init script launches. So that's like the main UI of the key. It's using DirectFB to handle the UI and the touch inputs. So everything is written out to the frame buffer. It doesn't have X or anything like that. It's just raw frame buffer. And if you check immediately, basically it exits when trying to run it in QEMU. But looking at the log, you can tell it fails because the battery capacity is listed as -1 instead of whatever the battery is supposed to be. So the key doesn't let you boot unless you've got a full battery. I guess they don't want you to unlock your car on low battery or something. So I patched out all the battery checks and a bunch of the other hardware-specific checks, mostly just with NOPS through R2, and now we have a fake full battery due to all the binary patches. And the main UI loads perfectly, and now I know I have like a working system environment for for the key to run in QEMU. I built Doom for ARM32, and it ran in my whole BMW key environment. I tested it; it works perfectly. I repackaged the file system and reflashed the Nord chip and plugged it back into the key and watched the screen for it to boot. And the key was completely bricked. I've got no debugging feedback so far. It's just basically all blind. It's probably not the best way to iterate because reflashing the Nord chip takes kind of a long time. And without any sort of like logging or any sort of feedback, I've got no idea what's really going on. I also ripped and teared one of the pads from the Flash PGA, so this key was totally dead. I still had like maybe 2 or 3 more of them. So so now it's time to like remove the entire AP and try to see if we've got any sort of debug ports that are on the rest of the key that I can mess with. So get the data sheet and start looking through to see what we've got for debugging tools. The data sheet for the CPUs it has JTAG and also something that's called the P switch. So JTAG sounds really awesome. It's what I want. I want to be able to debug the whole key, get some output. And P switch is also like probably a little bit more interesting here. The P switch is the pin that's used for recovery. So you basically just short the P switch pin, and it gets you into firmware recovery mode. It claims you need to put it through a resistor, but you can actually just short it, and you get the bootloader in recovery mode. So the key is basically unbrickable through software, but through hardware, it's obviously pretty easy to brick. So I took a multimeter, traced back through all the pins, and sort of mapped out how the entire how all the exposed pads are. So you can see we have all of the JTAG pins are exposed. The P-switch pin is exposed, so it's a relatively easy debugging platform to work with now. And I've got the full JTAG debugger wired up to the key. It's mostly pretty simple at this point. I attached GDB, everything seems to work. I can debug the whole low-level boot. When I attach, I dump the registers. I can hopefully single step. But it turns out breakpoints don't work. A lot of stuff doesn't actually work on this platform. I wasn't sure why. It says bad JTAG communication, but using all of the like default tools, it's obviously not working. So that's super frustrating, but it means it's probably have to go through a different way. So now I started to play with the firmware, which was like the sort of like the low-level boot of this. It's actually encrypted. If you run the p equals on it, you'll see it's basically random data, but the firmware in this key was actually encrypted with all zeros as the key. So I'm able to decrypt the firmware and start reversing it. You can see it's got some strings about battery voltage and everything here. So now I have all the firmwares, and I start reading through the NXP docs, and it turns out that they've got something that they call HAB, which is a high assurance bootloader, which is similar to like a secure boot on other platforms if you're familiar with it, which basically means the firmwares have to be signed. And I started looking, and there seems to be some bypasses for secure boot on these chips, but nothing that's like off the shelf or anything. But it also turns out BMW didn't even use this library, so there's no secure boot on the device. Any patches to the boot processor just work. I have their decrypted U-boot ELF, so I've got everything that I should need to continue. So the bootloader is U-boot. I can just modify this and re-upload in recovery mode. One way to mess with like a Linux system is changing the boot args. So it sets boot args in a few different places, like based on the boot flow. This is the boot flow that is like the normal boot. It sets a console, sets the root of the file system, and sets the file system type. So that's what we normally expect. But also reading from the ext2 file system, it has the RCS, which is the init script, and it checks if FTM is in the boot args. And then if FTM is set, then it actually it launches this FTM like debug binary. So I patched in the string FTM to the boot args, just binary patching that uboot. So it should have the special debug menu to make my life easier to debug it. And BMW also included the debug symbols for the FTM binary. They didn't strip it. It was fully symbolicated, so it makes reversing it super easy. So this is the main binary, the main function of FTM. It's pretty easy to see what the code does. There's a bit of a handshake where it says like sim wait for connected, and then once you're connected, then you get this loop where you basically read in a string, and then you call this parse string on it. So it does serial read, then chomp, then parse command. It basically looks like a CTF challenge from like 2012 in terms of quality. There's not even like storing and rewriting all of your notes app. So it's basically like beginner level stuff. We have the handshake here. This was from the wait for connected. You just write the string FTM alive over serial. It verifies that the string is equal to the expected one, and if so, it pops you into this debug shell with interaction. It's not really like a secret to have this FTM alive. I don't think that they intend this as a secret, especially because in the normal case you don't even have this FTM daemon listening. There's about 20 handlers or so. Most take no input. They're basically just like querying the status of the key, or like reading a debug value or something. Some take arguments, like this one is fill LCM color. It writes colors to the LCD for testing. So like if you wanted to see if you're able to write the color blue to the key, you'd say fill LCM color blue, and it will fill the screen with all blue. So there's a bunch of these that actually take arguments. This is one of them. And it's like the very simple stack buffer overflow. It calls scanf to the stack with an argument with the %s, and you get basically a free stack buffer overflow straight ahead right in the beginning of this function. It's like the very first time I tested it, I was able to corrupt the stack and crash the FTM daemon. I spent about an hour in the QEMU environment with the patched FTM binary to read from different place, and I got a working exploit. It works like every time in GDB on this, and then like a little bit later, I tried to get it working on the key, and FTM doesn't fork, and their stack ASLR. Even though it's a relatively old kernel, they enabled it. I'm a little bit lazy and didn't want to do any very complex stuff. But one crash and the binary is dead, and you have to re-upload the patched uboot over recovery again. Overall, it takes over a full minute for each attempt, which isn't great because like a full minute for everyone is it's too much. Like I don't have the patience for this. So I have to find a bit of a better way to get the code running. So the next idea was to take uboot, rebuild it from source, and add special handlers to search and replace files on the file system, and then boot it. Because I have control from boot, I should basically have the ability to do anything. But this hardware is not supported at all in uboot. There's support for this specific CPU, but there's no support for the memory, and there's no support for the flash. So I patched in support for the memory. It's mostly just from reading the datasheet about what you need to set, what pins you need to write to set it into this MDDR mode, and added support for where this needs to get loaded for the IVT and where the U-boot elf needs to be set. There's also, I added a few commands for patching the flash and for dumping and re-uploading the entire flash. So I had already done a bit of like forensics work to find what I wanted to patch. So there's a few things like patching in commands to load different kernel modules, like the serial kernel module and the Ethernet gadget, and also changing the Etsy shadow in order to get a shell here. So I patched, so I scripted U-boot to patch Etsy shadow and load the serial gadget kernel module and magically get some root shell over serial. Later, I did it through the Ethernet gadget, so I can actually just SSH into the key, but it's running like a very easy, like press a button, get a shell, and that's pretty nice. And to prove this, I've got a video. So I'm running a static build of Doom on the key. This was before I'd actually rewritten the renderer to take up the full size. So this was, I actually just had to chop off part of the video so it will render, because the key is not running at the full resolution of the of the normal Doom game. But there's a little bit of hacks around that in order to get it to work. Like I had to rewrite the way that the input is handled, because there's no keyboard device on this, and it's not a ton of effort in order to get Doom running, but it's relatively interesting, I guess. So now the key is totally owned from the entire boot process. Key firmwares are also not protected or locked to hardware, so I can clone one key to another. So if you're like trying to maybe steal a car or something, it's pretty easy to just take a key and with nothing invasive, dump the entire key and reflash it to a different piece of hardware. So I guess there's some theft implication, and this is totally unpatchable because BMW doesn't have any sort of update system. There's no like cloud supported update. And you can also clone keys from one model of BMW to another. So you can take what was a 5 series key and write it to a 7 series, or what was an i8 key and write it to a 7 series or something like this. BMW dealerships have a very expensive program for reprogramming keys, so it's like pretty unwarranted that they have that. I've never reported any of this to BMW because it's unpatchable, so it's kind of useless to tell them even. And a few extra like fun things from the firmware is they don't actually have any randomness. So the randomness is all generated from, they have this file that's called a random seed, if it exists. And out of the 5 keys that I've seen, every single key has the exact same Etsy random seed. So even though it looks relatively random, if every key has the same random seed, it's probably a bit suboptimal. And unfortunately, in 2020, BMW announced they're joining some like car kit key thing with Apple. So unfortunately, this hardware seems to be dead as of whenever that actually comes out, which I think is like soon. So even though the hardware is basically dead, it's still somewhat of an interesting platform to look at. So yeah, that's all I have. All right. And for questions, how do I go to can you disclose how did you manage to get a key without a car? People are generally selling these on eBay. They're about $100 for the key. It's I think maybe when people sell their cars, they have extra keys that they didn't give to the new owner, so they just sell them on eBay. is there any code in the key using the Giselle extension? Does QEMU even support it? I don't know. Probably not for code in the key using Giselle. They're using a pretty off-the-shelf BusyBox, which I don't think they even compiled themselves. So all of the userland stuff there is just like generic ARMv5T. The BMW MKD is all ARM native code. I didn't see any Giselle instructions in that. The FTM is all ARMv5T, so I didn't see any in that. It's pretty possible that QEMU does support it, but I never really looked into it because even though it's kind of fun to see this architecture, I didn't ever try using it. And I mean,
sorry,
yeah.
Do you want me to read out the questions?
Yeah, sure.
So, do you think that this can be modded to work on cars of different brands?
Possibly if they have the same RF frequencies, but most of the interesting thing of the key is that it provides data like your current battery charge, how much fuel is in the tank, and like the miles and how far you are before you need to perform like a maintenance or something. So you might be able to use it to unlock your other car, but you won't get any of the interesting data because it's probably not supplied in the protocol.
Cool. Another question? It is correct that the key also had UART pins. Why did you go with JTAG? It seems like in your pin description.
I didn't actually look at the UART at all. I thought that with the JTAG I would be able to just to modify U-boot as it was going and write to the boot arg strings. But once I was unable to continue from a breakpoint or do a breakpoint, I thought it's probably simpler to just rebuild U-boot myself and upload that. So it's possible that UART would work, but the simpler way is to just work with source code, I think.
Yeah, sure, if you have the source. Cool. Next question. Are there any other keys, fobs, that you're looking at next?
I don't think so. I think key fobs are a pretty boring target other than this one. Most of them are not doing anything very fancy. Like this one was cool because it's basically like a smartphone from 10 years ago. But I haven't seen any other cars with something that's really novel in the key fob, and this one is hardly novel because it's just basically like you went to Shenzhen and asked them to build you some touchscreen device and put your own plastic shell on it.
Yeah. So no one.
I think that's it for questions. Yeah.
This is the last one. Okay. Thanks. That was a really cool presentation and showing up also another use case for running Doom. So yeah.
And also, yes, I did run R2 on the key, but the resolution is too small to make it really useful.
Yeah, we need to make like a tiny UI for R2. I was doing that in some smartwatches, but yeah, I mean, it's not really practical.
Yeah.
So cool. Thanks for presenting. It was a really amazing job, and I hope that you can enjoy the rest of the conference.
Thank you.
Thank you.
Welcome to my presentation, Where's My Ransom? Hunting for ransomware gangs using r2 and Yara. Ransomware got a lot of news coverage in the past few months and years. Time by time I saw some reports popping up in all the different feeds I consume. In the past, ransomware was more a private computer problem. The user downloads a malicious file and gets infected. The infection vectors were different. Examples I noticed within my surroundings area were infections through torrent files, emails, and apparent cracked programs. Nowadays, we have ransomware targeting industrial control systems. An example is the ECANS or Snake ransomware, which got a lot of news coverage in 2019 and early 2020. In addition, ransomware groups make use of the European General Data Protection Regulation, or short GDPR. They steal data from victims, encrypt it on their system, and threatens them to publish everything. This would lead to a GDPR issue because most of the time personal data is affected in such leaks. One example is the Club group. They publicly list and shame their victims and even provide some parts of the stolen data to download. Next is ransomware as a service. Here, malware authors offer their samples in a dedicated business model. They sell source code of the ransomware or offer to deploy the malware of their customers on already infected systems. The security company FireEye reported that the Maze group even have a nice looking GUI to track all infections, see who already paid the ransom, and even allowed to hire pen testers to perform different steps of the cyber kill chain. Other ransomware groups switched their focus from smaller targets to businesses and organizations. This is called big game hunting. Even the FBI stated this as a problem in a public service announcement. All these different trends and new facets of modern ransomware caught my attention. But first I ask what has changed. For me, ransomware was always not that advanced. It just encrypts different files on a computer, blocks different ways for recovery, such as deleting shadow copy, and displays a ransom note. So I performed some internet research about different ransomware in the past decades. I want to state that the list is just an overview and not complete. To my surprise, the first known ransomware reached back to 1989. The AIDS Trojan was written by a biologist, Dr. Joseph Popp. The Trojan horse replaces the outer.exec.bat file. As soon as the boot count reaches 90, the ransomware hides all directories and encrypts the names of all files in the C drive. Afterwards, a ransom of $189 is placed. Next was Archivus and GPcoder in 2005. GPcoder decrypts different files on the victim's computer using RSA encryption. However, the use keys were kinda short. As a result, decryptors can easily crack them. Archivus first used more advanced RSA encryption with bigger keys. Due to this, decryptors have a harder job to brute force the decryption key. In 2009, Wundo was present. This ransomware is either a Trojan horse or a computer bomb. It causes pop-ups and advertising rogue anti-spyware programs on the victim's computer. In some cases, it even leads to performance degradation and denial of service of some websites. In 2011, Winlog was active. It displays pornographic images and demands a $10 ransom. It must be paid via premium rate SMS. After paying, the victim receives the unlock code. The people behind the ransom were arrested 1 year earlier in 2010. They reportedly earned over $16 million from SMS scam. 1 year later, the police ransomware was present. It also known as Reviton. This Trojan displays a fake notice from a law enforcement agency claiming that the computer has been used for illegal activities. As a result, the victim must pay a fine. CryptoLocker was active in 2013. It generates a 2048-bit RSA key pair for encryption. The ransomware threatens the victim that the private key will be deleted if the ransom is not paid. After a deadline, the price of the private key increased to 10 Bitcoin. In 2014, CryptoWall was in the news. It was distributed as a part of malvertising campaign on the Sido ad network. In this case, the ads redirects to rogue websites that use browser plugin exploits would then download the payload. This JavaScript payload is signed and looks like a trustworthy security software. 1 year later, Loki, TeslaScript, and KeyRanger were present. Loki was distributed using emails with Word documents containing malicious macros. Interesting is that the master key for the TeslaScript ransomware was published by the developers themselves. And KeyRanger was one of the first ransomware targeting macOS. Based on Palo Alto networks, it affected more than 7,000 Mac users. In 2017, big ransomware families made the news: WannaCry and Petya. WannaCry exploits a SMB v1 remote code execution vulnerability. The exploit is known as Eternal Blue and was leaked from the US NSA. It affected more than 230,000 computers in over 150 countries. Marcus Hutchins, known as MalwareTech, analyzed the ransomware and hosted the sinkhole, which is embedded within the malware. This stopped a lot of the infections. Petya aimed to infect the master boot record, so the next time the system boots, it blocks Windows from starting and shows the ransom node. GenCrab and SamSam were present in 2018. Interestingly, the GenCrab authors stated in January 2018 that they earned enough money and will enjoy their well-deserved retirement. They claimed that they made over $2 billion. SamSam targets JBoss servers. It uses a RDP brute force attack to guess weak passwords on the servers. Last year, Ryuk, Robinhood, Klopp, and Maze made the news. Ryuk uses a combination of AES and RSA encryptions or algorithms to encrypt the files. This makes it very hard to recover them. The Robinhood ransomware does not steal money from the rich and gives it to the poor. It rather targeted the cities of Baltimore, Maryland, Greenville, and North Carolina. As mentioned in my introduction, Klopp threatens to publish all stolen data from the victims, and Maze offers a ransomware as a service business model. This year, 3 ransomware families were of interest for me: Ecans, which I already mentioned in my introduction, Sudinokibi, and DoppelPaymer. I would say that Sudinokibi is kinda common when it comes to its used methods. However, they targeted big organizations and businesses. DoppelPaymer is a variant of BitPaymer ransomware. It attacked the city of Edcoach, Texas, and the Chilean Ministry of Agriculture. After I clearly saw that there is a big trend to big game hunting and the threat actors get more sophisticated, I set different goals to my research. First, I want to learn about ransomware and their evolvements within different families. Within those, I'm interested in finding new samples besides those already known to the public. Malware authors are software developers, and similar to any other coder, they really reuse source code too. You just don't have the time to develop every project from ground on. And if different functionality is already working for you, why not just reuse it? Similar to this, I was interested in code sharing between those families. Some blog posts point out that modern malware share code between different families. So if I write a Yara rule for a specific mechanism, such as the encryption algorithm, I would be able to detect other families if they share the encryption process. The last goal I defined is the detection of security incident or leaks based on VirusTotal uploads. Within security incidents, collected files must be analyzed to determine if they are malicious or not. To perform this classification, Aristotle can be used. So if a ransomware infection occurs, the company could upload all collected files to Aristotle. By using Aristotle's hunting features, I would be able to detect all the uploaded files. In order to achieve the goals, I need different technologies and tools to help me. I used Yara as a classification and identification tool of different malware samples. To not analyze each sample by hand, Yara allows me to quickly classify them based on a rule set. I will elaborate on Yara in the following slide. To use my Yara use, I used VirusTotal and hybrid analysis. Both allow to hunt for samples based on the uploaded rule. VirusTotal offers rich hunting capabilities. It includes retro hunts where all available samples within VirusTotal are checked, and live hunts where your rules are thrown against all newly uploaded files. If a rule triggers, you get a notification. However, VirusTotal is very expensive. Due to this, I also used hybrid analysis. You need to register an account for free to use the so-called advanced search. Similar to VirusTotal's retro hunt, all already uploaded files are checked using your Yara rule. In my opinion, hybrid analysis provides less hits compared to VirusTotal. To create the rule and find interesting features within the ransomware samples, I used r2 and keynote. Both allow me to analyze the malware in different detail degrees. On the one hand, to give me an overview of the capabilities, and on the other hand, to perform deep analysis of different functionalities in assembly. But first I want to give a brief introduction into Yara. As told in the documentation, Yara is designed to help researchers classify and identify malware samples. However, it is not limited to those intentions. On the right hand side you see a sample rule I wrote. In line 1 you find the keyword rule, the name of the rule and optional tags. It is important to give your rule a good and descriptive name. I personally use Kaspersky's naming convention, where each name consists of 5 parts. First, a description of the threat group. Second, the name, language or designator. Third, the threat actor name. Fourth, a description of the malware name or specific family. And fifth, the rule's intention. As a result, a sample name would be ransom _ZZ _TA505 _clop _encryption. ZZ just the place that no country, language or designator is known. Next is the meta section. It describes the rule and gives more context. Here I have 5 mandatory and 3 optional parts. The description, name of the author, creation date, reference and hash, if available, are mandatory. The TLP classification, the last modification date, and the version are optional. The third part of each rule is the strings section. Here you define the characteristics for the specific family or sample you wrote the rule for. I try to have 3 different groups of strings. First, unique artifacts such as mutex names, user agent strings, registry keys, and more. Second, a group of specific non-unique strings such as properties and structures, and sections and entropies and file sizes. And third, byte sequences. It allows me to have a good overview and structure of the rule. Furthermore, it is easier to define a good condition. This brings us to the last part, the condition section. Here, the trigger is defined in a Boolean statement. So which strings must be present to trigger the rule? In my exemplary rule, the strings r2con, is, and pretty must be present in the rule, or on the sample I'm testing it against. The byte sequence must be present too. The last section, here it is defined as x, should be not present in the scanned sample. So what did I do during my research? I first collected initial samples from blog posts and available incident reports. I downloaded the samples using hybrid analysis of VirusTotal and analyzed them in a quick manner. Based on my findings, I create the first rule to detect the sample or even samples if I was able to initially collect more than one malware. Next, I test my rule. For this, I have different test sets of about 5 million unique malware samples and 800,000 unique goodware samples. The rule should not trigger on the goodware set, but can trigger on the malware set. If I have hits, I check if they belong to the same family or if code was shared between the samples. If I get a lot of false positive, I have to improve the rule and test it again. The fourth step is the hunting part. As mentioned, I use VirusTotal and hybrid analysis to collect more samples. By using those, I am able to improve the Yara rule and create even better rules. If I feel I need more samples and the rule could be improved even more, I jump to step 3 again and continue from there. So let's jump into the demo part. I will show my process for creating 2 different rules, one for the maze ransomware and one for the Clop ransomware. Let's start with maze. I downloaded 3 different maze samples from publicly available reports about the ransomware. I use cut where I leave all analysis settings on default. To start with, I look through the string section and focus on unique strings and different artifacts I can find. At the beginning I see some runtime generated strings. Right afterwards there are Windows API and function related ones. This is very common for each MPE file you will analyze. At an offset of 100.151.E8, a lot of keyboard and language related strings occur, which we can skip for now. Next we have some interesting looking strings including Windows paths and even a PDB file string. This is always extremely useful for a Yara rule. Again, we can skip over the API related functions and the big strings containing nothing really interesting. And next, some really unique looking strings occur again. Although certificate related domains are common in PE files and therefore not really interesting for our Yara rule. We do the same procedure for the second file. It is also interesting to note that the symbols give some hints about potential Windows API calls the malware is performing. Due to this, different strings could be present. Identical to the sample number 1, we find a lot of runtime generated strings. Here we find a string that looks kinda odd. However, I'm not sure if it's runtime generated or not. I note it because its length is larger compared to the other ones. Right afterwards, there are some interesting looking NAN and SAN strings. I note them because they stand out to me. Again, we find some runtime generated strings in keyboard as well as language related ones and even 2 more PDB files. So that's it for this sample. Finally, let's look at the third collected sample. The symbols show some network-related API functions. Maybe we find some domains or IP addresses in this sample. We already know the runtime generated strings, however, some stand out to me. They look similar and are a bit longer compared to the other ones. I note them. Those strings look like UUIDs, although the structure is not how an UUID should be. It could be an ID related to this malware. Together with the hash looking string, I note them too. Again, we skip over Windows API, keyboard and location related, as well as the runtime generated strings. At the end of the file, we find a version and something Windows 7 Service Pack 1 related, which is always also interesting for our Yara rule. Before I write the rule, I check the different strings I found in a Google search. This allows me to spot obvious candidates or false positives, and I can also check if some are already related to the maze ransomware or other malware. In my Google search, I did not find anything odd. As a result, I will use all noted strings. Let's write the rule. For this, I use an editor, here Visual Studio Code, with the Java syntax package. I name the rule ransom_zz_ta to 101_maze_gen and fill out the meter section. I will not provide a reference because they are from different sources. Within the string section, I don't have any bytes. As a result, I create two different groups, S for unique strings and A for unique artifacts. Now I will fast forward over me filling out the string sections. I look for full words and the ASCII representation only. This usually gives me a lot less false positives for such strings. Finally, we focus on the condition section. I make sure to look for the MZ header, and the rule should not trigger on very large files. Therefore, the file size must be below 800 kilobytes. Unique strings can lead to a lot of false positives. Due to this, I limit them to trigger only if more than half of them occur. The artifacts are usually very specific and should not be present in other malware samples. Therefore, I want the rule to trigger if only one hits. I also make sure that the rule triggers if 18 of all the strings are present within one sample. After finishing writing the rule, the next step is to test the rule. For this, I use a tests set with approximately 800,000 goodware and 5 million malware samples. The rule should not trigger on any goodware sample, but can trigger on malware samples. If it hits, I must check if the sample is related to the Maze ransomware. The test itself can take a lot of time. Due to this, I fast forward the recording and show you the results. There were no hits on the goodware set, but I found some Maze samples in the malware test set. The rule is working as intended. The next step is to hunt for more samples. In the case of the Maze ransomware Yara rule, I use Hybrid Analysis Advanced Yara Hunting feature. I log in and copy and paste the rule into the corresponding box. As you can see, 3 samples were found. Some of them are already known to us, because they have the same hash as the ones we downloaded. But the first one, starting with 543F and ending with F47B, is new. By using this sample, we can enhance our Yara rule and find even more samples. Now we will create a rule for the Clop ransomware. Identical to the Maze ransomware, I was able to collect one sample from public resources. I will use cutoff analysis and Visual Studio Code as a notepad. First, I look through the string section and look for unique strings. As we already know, runtime generated keyboard and language as well as Windows API call strings are not interesting for our Yara rule. We skip them. Here we have the first interesting strings. Some look like file names such as autoexec.bat. Next we find a public key. This could be used for encryption. Right afterwards we find more interesting strings, including some mentioning Clop. Again we skip over all Windows API function strings and we find more referencing Clop. That's it for the string section. Let's take a look at the symbols. One stands out. It's keyboard, I get keyboard layout. I take a look at it because some reports state that malware will not execute on systems with specific keyboard layouts. Based on the assembly code, we can see that different language identifiers of the keyboard layout are checked. If one hits, the malware appears to take another path. It could be either excluding different languages or be targeted at them. In the Java rule, I will only check for one language identifier. The reason is that the order could be different on other samples. I could also look at for all checks separately, but I decided to only look for the first identifier, which is 0x437. So I note all opcodes and skip those which could differ on other systems. Examples are jumps to addresses and dynamic resolve data sections. I can use the question marks or the square brackets to determine random bytes. Similar to the Maze rule, I checked the strings in a Google search. I found nothing that pointed to potential false positives. As a result, all strings will be used in our rule. After analysis, we write the rule. The name is ransom underscore ZZ underscore TA505 underscore glob underscore gen. We fill out the meter section and get to the strings. This time we have 3 groups: unique strings, unique artifacts, and the opcodes for the keyboard layout. We fill out each group and make sure to look for a full word ASCII at each string. Finally, we look at the condition section. Similar to the maze rule, we check for the MZ header and the reasonable file size, which is in our case 800 bytes. 3 of the unique strings, 1 of the artifacts, and the opcodes, or 18 of all of them should work fine. The next step is to test the rule against our goodware and malware test set. We had no hits on the goodware set. This is good, and the rule does not produce any false positives and no non-malicious files. As a result, we can go hunt for more samples of the klirre ransomware. This time we use VirusTotal's retrohunt feature. We simply create a new retrohunt job and copy and paste the rule into the window. This takes some time. We can see that we had 1 pro match. Pro samples are older than 90 days. This means that there are either no klirre samples uploaded to VirusTotal, or the rule is not good enough and too specific. It is extremely unlikely that there are no klirre samples within VirusTotal. As a result, the rule is not good enough. I looked at the rule and noticed that I messed up the opcodes. It is too specific. Some of them can differ for other samples. As a result, I corrected it, tested it again against the goodware and the malware test set with no false positives, and uploaded it to VirusTotal. As you can see, the number of matches changed. Based on the results, we are able to collect more samples and hunt for potential new variants using the keyboard layout check. I also double-checked the improved rule in hybrid analysis Yara hunting feature. Here we had 32 listed files. Some are even tagged with Lokagoga, which is another ransomware. As a result, they share potentially the same keyboard layout check. Let's summarize everything. I was able to learn about ransomware families and their specifics. I was also able to find new versions and additional samples of the families I wrote the Yara rules for. I was not able to detect code sharing between families I looked at. And I'm not sure if I can match big upload chunks to incidents. Sometimes I have one day where up to 50 uploads for one family occur in a short period of time within VirusTotal. This could be related to an ongoing incident. However, I'm not able to match those days with leaks or incident recorded in the news. After seeing in the demo part of this presentation, I failed multiple times. Based on those, I have 3 things I learned. First, test your rules properly and on a good test set. Use unique strings or not just strings that look odd. And don't get too excited and think about opcodes. I want to thank you for your attention and the r2con staff for organizing this awesome conference. Each year it's a blast and I learn a lot of new things. Sadly, this year I'm not able to connect to you in person, but hopefully we will see each other in the next year's conference in Barcelona. Have fun at the rest of the conference and keep reversing.
Hey, so thanks for your presentation. It was amazing. I don't know if the team have any questions for your talk.
Yeah, guys, I made a mistake. The link was not accepting questions, so please, I allow it now. Feel free to send the questions.
No one was complaining, so we'll wait a little bit and see if someone is.
Yeah, sorry for that. Let's give it a couple of minutes.
Sure, I have a question. So for the Yara rules, how do you manage them? I mean, do you have like a way to because usually when people works with Java rules, they use or they need a way to select them and group them by different tags or descriptions or different operating systems. You used to manage them all like in a single big Java file, or you compile them by separate, or you use the blobs, or you create like different sets for them?
It depends on the Java rule itself. So, for example, if I use the naming scheme I presented, where I have at the last section, the part 5 of the name, what the Java rule is basically doing, I have one Java rule for one specific algorithm, for example. So generic to match a generic sample, or like keyboard to look for the keyboard check. But usually I have one rule for one specific method which I want to look at. So not one big rule where one big Java rule where different Java rules are included, because I think there's no reason for me to scroll through everything and find it again, and it's easier to document it.
Yep. Cool. So, is there any question? Yep, you have one. So, what goodware samples that did you use for benchmarking the rules?
Basically, Microsoft binaries, where you can just download it from the Microsoft website. And also different binaries I found from universities, and also some just software I use commonly, for example, browser.exe files or browser.bin files, and different stuff where I definitely know that this is goodware, or this should behave as goodware. Yeah.
There are more questions?
No, this was the last question for the talk.
Okay, so yeah. So if there are no more questions, we'll probably close the stream and go for the waiting a scene and switch to the next presentation. Thanks, Kevin.
Yeah, thank you.
That's a great presentation. Well, actually, I have another question. Because I've seen some people writing some R2pipe scripts to automate the auto-generation of the Java rules.
Yep.
But I don't think there is any way to automate that in a perfect way. I mean, there is always a need for humans to clean up the rules. And
yep.
So do you have any approximation or any hints to improve this kind of filtering?
So I've just seen some presentations and reports from Kaspersky where they generate their Java rules automated, but they have to check them too. And they automatically check them against their test set. So for example, if it tests against a goodware sample or hits on the goodware sample set, it's automatically piped to a human. But a way to check it automatically and determine if this is a good Java rule or not, I don't know if there's a good way to do it. I think at the last resort, always a human have to manually look at it, because with Java you can generate a lot of false positives, and I've seen some people deploying them within their company and then aren't able to receive, for example, any emails with a specific attachment, which is goodware, because this one goodware sample wasn't in the test set. In my opinion, it should be treated carefully and an alert. If you hit something, it's way better than just blocking it. So you basically have to check it.
Okay, thanks. So, okay, if there are no more questions, we'll go into the waiting a scene. Thanks for having it and coming to the conference and speaking here. It was great to have you.
Yeah, thank you for having me.
Thanks.
Good evening, R2con. And let me just double check that this is working now. So we had some little bit of challenge getting the stream up and running. Normally we meet in Barcelona. Tonight I have the honor of welcoming you to Oslo, where we are trying our best to live stream on YouTube. And I'm getting some confirmation that this works now, which is amazing. Perfect. This is also the first time I'm doing a stream. So, okay, perfect. It's kind of hard to do the presentation and all the technical things at the same time, but I will manage. So back in 2017, maybe some of you remember, I gave a talk on an I/O plugin I wrote for R2, where I wanted to turn the r2 framework into a hypervisor debugger to basically debug code running on a Windows machine for purposes of malware analysis. So unfortunately, that was never released, but I'm here today to announce to you that we are we are giving rebirth to that project with a startup that we have recently started. And today I will announce that we used to be called OX Epic. We have decided to change our name to Flip Reversing because I kind of like that name. So for instance, right now we're working on the backend, which we call the backflip. We are soon to hopefully be working on the front end, which we plan to call the front flip. And tonight I will demo an early alpha version of the R2 debug plugin that we call the hyperflip. So first, let me just do a little bit of a background on the malware landscape and why we're doing this. So if you look at what's going on in the world of malware today, there's about 350,000 new malware threats per day, according to AV Test, which is a testing organization that operates in the antivirus industry, basically. And so the challenge then becomes to understand the threats that matter to you, basically your organization. As today there are targeted attacks, and there are probably all of those 350,000 threats will probably not matter to you. So you need to basically, as a security organization, you need to discover the malware threats and actors that can hurt you. And you need to handle the malware threats that can end up causing security incidents. There are some challenges related to malware analysis. Basically, if you are to analyze even a percent of a percent, which is referred to as a per myriad, of 350,000, that would still mean you need to analyze 35 files per day. And knowing that a single threat can easily take up to 2 weeks to analyze, if you look for the most sophisticated threats, that just doesn't scale up very well. And also knowing that the more sophisticated samples typically actively try to evade our analysis, that just doesn't make the situation any better. So for me, when I've been doing reverse engineering and malware analysis, for me, reverse engineering has always been about trying to find a combination of dynamic and static techniques in order to be as efficient as possible. So you can say that basically dynamic analysis is a lot faster, and although it's not as accurate as static analysis, then sometimes it's actually enough. But regardless, almost always it is useful for like the deeper analysis. So whenever I have a sample, regardless of if I'm doing that in more of an incident handling scenario or something else, I typically start out by doing like a dynamic analysis of it before I jump into sort of analyzing the details of it. So you want to get an idea of what the code is doing, and you want to basically look for and locate the interesting code that you want to analyze further. So that's basically two typical things I want to achieve when doing kind of a dynamic analysis. So we have this concept called evasive malware, which is kind of like an anti-analysis thing, where basically the malware authors or whoever is using malware basically does this to frustrate reverse engineers by actively making analysis challenging. So typically this will be a combination of code obfuscation / encryption, to make static analysis hard, and then you combine that with something like a virtual machine detection or a sandbox detection, which can be looking for the specifics of a virtual machine itself, or it can be looking for specific analysis components within the sandbox. But it can also be things like checking the IP address, like your keyboard layout, if you move the mouse too fast, if you move the mouse too slowly, if the screen resolution of your desktop, and there's like an infinite bag of tricks that they can use. And then there are some more generic techniques, such as self-debugging, where you basically debug your own program, making it impossible for an analyst to attach his or her debugger. And finally, we're seeing a lot of use of what I typically call multi-stage code injection, which is basically spawning multiple processes, injecting code into some of them, maybe ending up injecting some code into explorer.exe, and then you end up trying to debug explorer.exe and everything freezes. And so it becomes challenging to kind of locate the interesting part of the code. Yes. So if you look at the current available solutions for malware analysis, typically you would use a malware sandbox as your initial step for doing your analysis. These are quite nice because they will give you within 2 to 5 minutes, you will have a report, and you might get an idea of what's going on with this thing. So I highly recommend using it. The kind of the drawback of this is typically that the reports are quite superficial. But more challenging is the fact that evasive malware typically don't run very well in there. And as I put in the slide, basically all fully automated analysis solutions will be vulnerable to evasive malware, always. I mean, there's no fix for this, because there are simply too many tricks that they can use in order for an automated sandbox to always produce the correct results. And if you want to properly solve the anti-evasion problem, you need to solve the halting problem, essentially. As far as I don't think that's been done yet. So with the flip.re project, we are building an interactive malware analysis system where we combine dynamic and static techniques to basically enable analysts to analyze the advanced threats faster and enable them to triage threats faster. So basically, we enable them to analyze the most sophisticated threats, and we enable them to more quickly get an idea of what's going on so that they can prioritize better. So basically, you need to understand how the malware works before it's too late. If you have an ongoing attack and you spend 2 weeks analyzing the threat, but the adversaries are done after 2 days, then you're too late, basically. And my other claim is that you always will need a human in the loop, because it's impossible to fully automate malware analysis. So let's talk about the plugin that I've been working on for the last over summer and a little bit before that. So the plugin is an IO plugin for R2, kind of similar in concept to what I presented in 2017. It aims to turn R2 into a hypervisor level debugger. This means that we want to debug code running inside the Windows guest from outside of it. So it's enabling us to debug code in a very sneaky and stealthy way. I'm not saying it's the perfect solution to anything. We can definitely still be evaded, but it's sneaky and stealthy. So for several reasons, I had to write this thing from scratch. And over the past few years, I've been slowly learning Rust. So for this plugin, I've actually coded the entire thing in Rust, which I just want to say a few things about Rust. I think it's an amazing language. It's one of those things where the more I use it, the more I like it. I think it has like an amazing like modern tool chain. It's so much nicer to work with their build system Cargo instead of having to use the make files and things like that. So I would claim that it's like a great replacement for C as a safer and more reliable systems programming language. But I mean, it's both you get the benefit of it being harder to exploit, so there should be less vulnerabilities in it because of how the language is designed. And also, once my program is accepted by the compiler, it typically works. So you don't get as many segfaults as you can do when you write C code. More on the con side of the fence, the compiler can sometimes feel a little overly strict. So it can be a little bit frustrating sometimes, and you feel you're fighting the compiler a little bit. And also, unsafe Rust has a very similar feeling to C. So if you end up writing a lot of unsafe Rust, basically like a low-level Rust thing where you can dereference raw pointers to memory, you end up doing a lot of typecasting, and you end up doing basically memory management. So you need to keep track of where you allocate to some memory, and then you basically have the same challenges as you do in C. So also when I developed this thing, there were some segfaults. But basically what you want to end up doing is you write most of your logic in C, and then you write like a thin unsafe Rust layer, and then through that you can communicate with all this C code, basically. And this is how I did that for interfacing with the R2C plugin API. I'm using BindGen to do this, which is very nice. I absolutely recommend it. So the way you do this is basically you have your build RS file that is run whenever you compile the program. And then I'm compiling the plugin on a system where I already have R2 installed. Okay, so basically I'm pointing the my compiler to the whereabouts of a few header files, and then I'm giving, which is like .header R2 wrapper thing. I'm giving some Clang args for it to understand like where to find the installed libraries on the system. And then the thing that I really like about this is that you can whitelist the things that you need only. So what this ends up doing is basically generating Rust code, where like the input of it will be C header files, and the output will be Rust code, like glue code for your Rust program to work and interface with and link against the C library. And instead of generating Rust code for the entire R2 universe, you can just whitelist like the very few things that you actually need, and that's how I really like that. So in this example, you see I use some variables, some types, and some functions, which is also quite nice because it's by doing this you can actually call some R2's C functions from your Rust code, which is a really nice thing. If you do this, then basically you end up with a plugin in Rust that looks something like this. If you're familiar with the C API, then you will probably recognize this structure. It basically defines like the name and the version and things that if you do an R2-L and list the plugins, that's what's being shown. And it enables you to basically specify the callbacks that the R2 framework will call in various scenarios, such as check to see if this URL should be opened by the plugin, closed and the close, open, read, and the system callback, which we use for enabling us to implement our own commands. So not like super advanced, but I think I really like this how it works. And the other thing is that you can actually compile C code together with the Rust code, which using the CC crate, which in this example you can see I am reusing some of the GDB logic that already exists in the R2 shared library. Basically, it's a kind of like a temporary thing because I had to cut some corners in order to get a working plugin in time. But it's really nice, and I think it just gives you just to have the possibility of actually including C files and then compiling that into your Rust code is just a nice kind of freedom. So I wasn't quite sure how to do a plugin in Rust. It's kind of challenging because there are so many details. So what we decided to do is that after the con, I will release a Rust plugin example. So if you're interested in learning more about developing plugins in Rust for R2, then follow us on Twitter for some updates at Flip Reversing, and have a look at our GitHub at github.com/flipreversing in a few weeks' time. Yes. So let's briefly discuss the architecture of our system and how the plugin interacts with QEMU and how it does that in order to debug code running inside the Windows VM. So there are three key components to this. Firstly, you have the GDB protocol that provides us registers and debug control, essentially. So QEMU is running on top of the KVM hypervisor, which has a Windows VM running on top of it. And through the GDB protocol, we can control the CPU, essentially. I'll come back to this diagram in a second. I just want to quickly discuss how GDB works. It's actually quite simple. You add a -s parameter to QEMU. That enables the GDB stub, which is the GDB server on localhost 1234. Okay, so this effectively enables us to debug the virtual CPU. So through this protocol, you can query CPU registers. You can do things like single-stepping the CPU, and you can make QEMU trap, or basically stop, when it encounters a breakpoint that we put there. So that's what we use it for. So coming back to this diagram again, the next thing is basically the shared memory that we use to provide access ultimately to the virtual memory inside the Windows VM. But first we get access to the physical memory. So the way this works is QEMU has a concept known as a memory backend file, which enables you to share the physical memory of the Windows guest with the host. So if you run QEMU from the command line, you can pass it this thing called the -object memory backend file. And I've redacted some of that, and then you specify a mem path, which you can see I've set to a dev/shared memory/flop, since that goes well with the flip. And this enables basically the something running on the Linux host to share memory and basically read and write to the guest's physical memory. Okay, so on top of that, we perform the translation logic. So obviously, having access to physical memory is not really useful. You need to work with virtual memory inside the Windows guest. And the way this works is basically each process has its own CR3 value, and these that's what we get from GDB essentially. Actually they have two now after the Spectre meltdown thing, but basically it's one for user mode and one for kernel mode. But regardless, these values will basically contain the address of the first layer of the translation logic, which is called the directory base table. And the x86 architecture defines the address translation logic, and then Windows adds some stuff on top of that, which I will not go into details tonight about, but you can, I did talk about that to some lengths back in 2017. And you can also, for more information, you can reference the Intel instruction manual and the sysinternals books. They also discuss these things. So in summary, our plugin will enable us to basically select individual processes to inspect and then effectively work with virtual addresses. So the last final piece of the puzzle here in our architecture is access to the PDBs, which are the debug symbols that Microsoft has available on their Microsoft symbol server. These PDBs are basically the are key to navigating the Windows kernel. And as I put here, it's essentially our API. It's a non-existent API to the Windows kernel, essentially. So it contains details on the type, layouts, and the structures, and basically, since there's no API to use, a lot of these structures behind the official APIs, they are undocumented and they typically change over time. But they're in the PDB, so and also it gives us the location in memory of some very important structures, so that we are able to do things like finding the process list in memory. So those are the three kind of main components. So the only thing you need to download the correct PDB for your kernel is basically the GUID, globally unique ID, which you can parse from R2 using the I command and grepping for GUID. And then you need the PDB name, which you can also get from R2. And with this information, you can basically download the correct PDB from Microsoft. That's what we do. And then finally, we parse the PDB using the PDB traits in Rust, actually. I know that R2 also has PDB parsing logic, but we ended up using this one, which is a really nice trait. I have some good experiences with it. Okay, so let's try to do a demo. This is a live demo, so if you want to say something to the demo gods, then now's a good time. So what we'll do now is I have a Windows VM running. We will attach to it, and then we will load some kernel symbols as flags, since we already have access to the PDB files. That's possible. And then we will load a program inside the Windows VM with some help of Frida. So here we go. This is a Windows 10 VM, and there's nothing special about it. It's just a normal VM with no modifications. And then from the outside, we can launch R2. So firstly, we can list the installed plugins. And you can see here I have my Flip plugin installed. So once the initial setup is done, you can easily attach to the Windows VM using this syntax. and then you give it the name of the shared memory file on the host. And now you can see it's connected to the shared memory for access to memory, and then it's connected to GDB in order for debug control. It will list that it's running a Windows 10, and the current process ID running on the CPU right now is 4, and the thread ID is 0. So up here you can see this Windows VM is now frozen in time and space. The mouse does not move. In here we can move around, enter visual mode. We can see what's going on, and if you do remember back to my demo in 2017, this is kind of a similar place. But the point here is sometimes not easy to navigate the kernel without symbols. So if we do this, load kernel symbols, that's a command specific to our plugin. It will load the symbols as flags in R2. So, and you can see that we are actually in the how processor idle place. And just the fact that you have all these symbols, it just makes it so much easier to know what you sort of navigate around in the kernel. Cool. Now let's launch a program and let's start debugging it from its entry point inside the Windows VM. So if we allow this to continue running, I told you I wanted to do this using Frida. So in here, when you're ready, Windows. Okay. And I have my Frida server here. So basically we tell Frida to listen on this IP, the local IP. And then I've set up a tunnel basically from my host via QEMU into the VM. And then from the outside, we can now run Frida. So I have a program in here, just for fun, I call Granny Teeth, which is a program we will be running. Now, Frida will start up and spawn the process, but you can see Frida tells you that you need to use resume to let the main thread start executing. So at this point, Frida has loaded the program, but it's like super early in the process creation process. So the entry point of this Granny executable is not yet executed. What we can do, we can connect this VM now and have a look around where we are. We can list the running processes using DP. So these are all the processes that are now running on the system. And we can, a little bit of delay, we can look for the Granny process. As you can see, Granny Teeth executable is here at PID 2372. Now if we select this process, the registers will change to the stored context register. So whatever the registers were the last time this executable ran, essentially. We go here and we load kernel symbols again. We can see that we are inside PSP user thread startup, which is very early on in the process creation process. Okay, so if we wanted to actually run this to completion, or basically start debugging it at the entry point, what we do is use the DMM command, since we now selected the granny process. Using the DMM command to locate all of the modules, you can see the executable image. You can also see that Frida agent has been loaded into it. Since the entry point resides within granny teeth, we have a command \e, which will parse the PE header at this memory location and give us the entry point of the executable. We seek to that address and oh, there's like a delay. That's annoying. And here we are. My OBS is lagging my thing. So here we are now at the entry point of the granny process. And from here we can put a breakpoint. And then we go back and we let the VM continue. So the Windows is now unfrozen. And then we can go down here and then tell Frida to resume again. And then we can see our breakpoint hit at the entry point, and this VM is now frozen in time and space again. And we can go in here and we can see that our instruction pointer is now at the entry point of this executable. So that enables us to start debugging this specific executable from the outside, essentially. So if we just let this go now, we shall see the program starting up. And you can see that there's a program telling me, oh, hello there, Frida. I am your grandmother. My teeth are huge, but this is normal for my age. Okay, so which takes me to the next part and my last part of my talk. So I wanted to do a quick case study, as since I mentioned that evasive malware can be a challenge. My claim is that tracing can be an extremely efficient technique to locate interesting code. And for instance, you could use Frida to do this. It's an amazing tool. But the challenge is that if you are a malware, you can check for Frida's processes on the system, and then you can decide to evade our analysis. But our system can basically hide analysis components from or tools like Frida from the malware, and in this way we can sort of fool the malware into running. So just to quickly explain how this thing works is when you're retrieving the process list in Windows, the process list is located in an encrypted memory area called the KD debugger data block. But basically the PDB contains the keys we need in order to unlock that, or basically de-scramble or decrypt that data block. Inside the data block, there is a pointer to a process list. And then in memory, you will basically have a list of processes as a doubly linked list, which becomes like the ground truth for everything in Windows. So it doesn't matter if you use like a high level API to query the processes, or like more of a low level. If you use like the create tool help snapshot 32, or if you use like an NT query system information type of call, the information to all of those APIs in Windows are essentially retrieved from this list in memory. So if you wanted to hide this Frida process of ours, the one way of doing that is to use an ancient, it's a rootkit trick, essentially. So basically you have a linked lists of all the processes, and you can see Frida being here in the middle. So we unlink that simply by updating the pointers of the element before and after it in the list. So basically this next pointer will now skip over Frida, and the next one's previous pointer will also skip over Frida. So that should be enough for us to hide the Frida server Frida server process on the system. Let's try to do that using rootkit techniques to hide the Frida process. I'm fooling grandma into revealing her true self. And if I have time, I might do that twice, actually. So you can see here our Frida server process is still running. Here, Frida server. And now let's start Frida again. I want to do the same thing as I did last time, basically start this Granny program, then hide the Frida server process, and then hopefully Granny will reveal herself. So we start Frida. And we pause the VM. And now in here, we can look for the Granny process. Or not. Select the, we look for the Frida process. So you see Frida server is here. And basically we grab the process ID of Frida server. And then I'm using a command I implemented called hide process, which has, for demo purposes, some extra things in here where you can explain what it's doing. And you can show what it wants to do. Basically, it's generating commands for me. So it's generating an r2 command, write value something at something else, which is these two updates to the linked list that I want to do. If you do this and execute, basically I'm having my plugin execute that command that it generated. It says Pete1816 is hidden. And then it gives me some idea. If I want to undo that, then I need to run a different command. So now we should have this VM unfrozen, and then we just resume the Granny executable. And it says, I am a wolf. I will eat you, om nom 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 nom. So you can see that clearly this is an example of something that is looking for the Frida server process and then behaving differently. But we can do some tricks on the outside and sort of just fool it into running. Funny. Let me do one more. I think maybe I'm running out of time. We can try to do one more. A similar one. I have also a Granny nose executable. But if we run that inside here, you can see it's also It's also detecting Frida, essentially. Sorry. But in this, basically, it's a similar technique, but instead of detecting the server process this time, it's actually detecting the injected DLL. So in order to get around this, we will need to basically, just similarly as we did with the server process, we need to basically hide Frida's injected DLL into the process. So if we start the granny nose again, and then we find the granny process, granny nose EX, and we select it, obviously. So whereas the server, the process list is obviously unique, as in there's just a single process list for the entire system. But obviously, for the module list, there's like one module list per process. So we select the granny nose process, and we use the DMM command. This will again list all of the modules in granny nose. And we can see Frida agent is loaded here. And then we can use our hide module command, passing it the base address of Frida agent. And for demo purposes, we can show it like this. And you can see it's, I say you can see. It's larger than the other command, but basically, sometimes Windows is just a little bit more complicated, but it actually keeps 3 different linked lists in memory for the modules. One is called in load order module, or the other one is called in memory order module, something, and then it's got in init order or something. So we need to hide the Frida DLL from all of these 3 linked lists, essentially, and that's what this command does. We do this and then just execute. That command will now be run by R2, and it says that our module is now hidden. So this is, we actually also hide it from ourselves in this case. So you can see if we actually list the modules again, then Frida has disappeared. Oh good. And now we can let the VM continue, and we resume Granny. And lo and behold, Granny is now a wolf. So so again, it's a similar ID as in hiding the process list. It's just you can hide stuff from the outside, and you can fool things into running this way. So as my final trick, just to be funny. Let's say you wanted to do something crazy, because you can more or less do anything from like this level. If we go into our process explorer here, when we find the system process, we can see that the kernel is loaded. So just for laughs, I wanted to just demonstrate that if we wanted to, we can also hide the kernel. So in here, we go back to R2. I have a command called -k, where we switch to kernel mode. And now the DMM command will basically list all of the loaded drivers on the system. And in here we can find the anti-OS kernel executable, which is the kernel image. And then we can similarly run a hide module command. Show. In this case, actually, it's only a single linked list for kernel drivers, so it's in a way I guess it's simpler. And we execute this, and now if we go back, unfreeze the VM, let it run again, we can see that the kernel no longer exists. So Process Explorer is now not able to find the kernel anymore, which is maybe a little bit concerning. But yes, that concludes the demo for this round. So I wanted to reach out to all of you lovely R2 attendees and tell you that we hopefully will be looking for some alpha testers and early adopters soon. So if you're interested in these things, then follow us on Twitter at flip.re. You can join our Telegram or send us an email and just get in touch with us. We're still really early on in the process of doing what we plan to do, but I believe in working with potential users. Yeah, feel free to reach out to us. And if there's time for questions, there's like a URL on top which you can use, and I should hopefully see it. Oh yes, there are questions. So let's see. Okay, time for questions. Good. Okay, so this is a question: how does AV test define new? Honestly, I don't know. These are just some numbers I wanted to use to illustrate just like the fact that there's like a large volume of malware out there. It also like very much depends on the type of malware. Like, so it's, yeah, obviously not all of those 350,000 are interesting. But I guess you would have to ask AV test for more of the details. Yeah. Okay, so what's the purpose of having additional plugin between R2 and GDB protocol instead of R2 using the GDB protocol directly? So basically, I'm using the GDB protocol, but not exactly like the GDB client would use it. Actually, the protocol is slightly modified to include some additional registers. So it's basically, and also the plugin needs to combine information retrieved from the GDB protocol with information retrieved from the physical RAM in order to make sense of things such as virtual memory inside the Windows VM. And this is a very good question. Is this stuff open source or will it be? So we are hoping to make as much as our software open source as we can going forward. That being said, we had not made a final decision yet, but hopefully my hope is to release at least a plugin as open source. And then there's this question: won't evasive malware also detect reader? Yes, but we can hide. I guess maybe that question was asked before I showed how to hide it. Does module and process hiding not cause problems by also hiding them from OS functionality, which is supposed to use it? Absolutely can. It absolutely can. I think you need to be really careful when you do things like this. And it's not as easy as I just kind of portrayed it now, I guess. Since if you manipulate these types of lists, for instance, the process list, and you fail to undo those changes, for instance, just by terminating the process, then there are like integrity mechanisms within Windows that will basically trigger in a trigger and then effectively just blue screen the system. So absolutely. So you need to sort of work your way around things. But my point here is more that we will be able to do things and basically fool code into running. But yes, it can have side effects. So. I think. Oh yes, this one good. Frida has other detectable side effects, other than the presence of its processes in the list, which I absolutely agree with. And there's like, as I said earlier, there's like an infinite amount of things you can check for. So typically, how I would perceive doing this is that you would do some type of analysis, and then you would interactively hide the things that you need to. Because I don't think there's like a single silver bullet that will enable everything to run properly, but instead you can basically perform some analysis and figure out what you need to change in order to reveal the hidden functionality of the thing you're analyzing. Okay, so with that, I would like to thank you for listening to me, and you should absolutely enjoy what's coming up next, which is the Chiptunes party, which I'm really looking forward to. So take care, see you soon, and toodaloo.
Cool, thank you. Thank you, Lars. It was an amazing presentation. I hope you all like it. We're a bit out of time, but we're still quite fine. Much easier than organizing in a physical place. We'll close the stream for 5 minutes or so. So I will set up the next scene for presenting the closing keynote. And after this, we will start the Chiptune concert. So stay tuned and see you soon. So this seems to be over. This is the closing keynote of the r2con 2020. It was an amazing experience for all of us, not just for the organizers, but also for the speakers, as well as the organizers of the competitions, as well as all the attendees that have been sharing their questions, feelings, and following all the talks all the time. We tried to make everything as better as possible, so trying to have like the feeling of being in a physical conference, but staying on from home. And we will all wish to be together in the same place and be able to continue the way that we have been doing the conference like in previous years, but this was impossible for this time. Anyway, this is not the end. Thanks everyone for watching the conference. The conference is over, but the party will continue after this. We will first announce the winners of all the competitions, and then we will jump into the Chiptune party. But after this, you can keep coding and reversing. Well, if you are curious about how we prepared the conference, you can check out the repository with the r2con2020. There is like a README file that describes basically all the stuff that we have been doing behind the scenes. There is probably more work than the one described in the list. But yeah, I hope that all the hard work that we did and you didn't saw that, it was good for all of you. Apart from that, we also hope that you enjoy. We will share you one poll to get some feedback from all of you so we can improve for future editions. And well, actually, we posted one of the polls asking you if you want to keep the full streams online available, because the plan was to stop them to be public for 2 days, so waiting for Monday. But everybody was at least expecting to have it for 1 week. We want to process them and put some index subtitles and giving some proper links for indexing all the talks and all the presentations. And the cool thing is that YouTube recorded everything, so you don't have to worry about missing any of the presentations or the talks that we have been doing in the conference. So after this poll, the results were quite clear. So we'll keep the videos available for a week. So this is after Sunday 30th. We will edit whole 4 days on stream, and we will try, and this will take a while. So meanwhile, you can check the public streams and follow also all the videos like we did these days. So first of all, we want to congratulate all the R2Wars winners. It was an amazing year. There was like a lot of people playing this time. They was also having some fun, and so we are having like a bunch of new competitors that they were quite happy about participating in this game that they didn't play before. So I will name the 3 of the winners. They all played with ARM, 2 of them with 32 and another one with 64. So there is basically the first winner, which is Flacucho. You can check the Twitter, which is the Goyo 2600. The second bot that won the competition was Anisse. The Twitter handle is AISSN. And the third position, but it's not actually third position because it was having the same score as the Anisse, it's Flagbot. And Flagbot was written by Cyanpencil, and actually he used ARM64 instructions. And actually, the coolest thing of his bot is that it was the first time that he was participating in this competition. So it was a great experience for him, and he had a lot of fun. You can also check out the video because he was presenting the bot and explaining the techniques that he used in there. And finally, we have a special mention for Niku. Niku is the bot written by Kurt. He sent this bot the second day of the conference. Well, this bot was actually exploiting a vulnerability in R2Wars. This vulnerability was basically being able to write all the memory in a single cycle of the CPU. And as long as the way that the R2Wars game is working, it was enough time basically to get all the rounds winning. So we managed to make a quick fix for this issue and make another run after this, and the bot was not winning after this. So anyway, even if it was not winning at the end because it was exploiting a vulnerability, we want to appreciate the work and all the research that he did while playing on the game. And we will send the merchandising pack to all the 4 participants that won the competition. Not just this, also we want to thank all the other participants. You have a screenshot of the scoreboard, the final scoreboard in the slide. And well, I would like to thank everybody for participating in and having fun. And I hope that maybe next year we can probably organize the R2Wars competition, having like a physical as well as a virtual environment playing together. After this, we will speak about the CTF competition. We have Murphy in line, so he can speak about that.
Hi, thanks, Pancake. First of all, I just want to mention that 219 users were at least registered to the platform. So thank you to all of you, because it's a bunch of users, at least trying one or two challenges. So thank you for participating, because I mean we do that for all of you. So it's just a pleasure to have so much users trying to reversing and enjoying that game. As well, just something to mention, it's about the results of the challenges. It's just awesome that there's only two challenges that were not solved, that are the r2PM2 and the master key, that is the r2pay application. There were two hard ones, and that the exit, that is the one that was in the easy section, was the most solved. So just here, as you can see, there's just, it's a good distribution of how many solves you did it. So congratulations for all that you do. You just solved the games. So for the next slide, just to mention the CTF winners. The first place, it's just Punk Not Dead. The second, it's Wreck the Line. And the third place, it's Barco. So just congratulations for the winners, that they just solved at least one hard, and so many mediums, and as well a bunch of easy games. And they did it pretty well. This year as well, the scoreboard was changing all the time, so it was quite interesting to see how the first place was just between different kind of users. So congratulations for the winners. Remember that some of you already sent the write-up, but just remember that you can do, you need to do that just to claim your prize. And congratulations. It's what it is. And just to finish, just congratulate to all the organizers and developers of challenges, that without them, the CTF wouldn't be possible. And as you can see, there's a lot of people just challenge you with all the games that you had the opportunity to try it. So thank you to all of you, and thank you to all the players, because from the organization we enjoy it a lot. I hope you did it as well. So thank you. Okay, so Pancake, yeah, your turn, I think. Sorry, it's the turn of Paul, I think. That it's
Okay, so the talks are finished, but we're in the next few minutes, when this closing message is finished, we are going to start a new stream, and all of us will be able to enjoy the awesome chiptune music from the 5 artists that will be joining this year, the Chiptune party. So many thanks to Edge, klirre, Alex Wiklund, 40boy, and neuroflip. We have been performing these chiptune parties the previous years as well. Of course, it was a lot of fun when we did it like in a physical place. Unfortunately, this year global pandemic is not allowing us to meet, but We will prepare like the stream in a few minutes, and please grab a beer and enjoy the music, and clap very hard for these musicians that are playing for us. Pancake. Okay, at least can you move to the next slide? Yeah, we are experiencing technical difficulties and Pancake cannot speak. 1 sec. Yeah, okay. Look, Pancake, listen. I muted you because you were making noise with the keyboard, and the Google Meet is not allowing me to unmute you.
Okay, fixed. So thanks to everyone. Basically, with all of you, this event wouldn't be possible. So I would like to give a huge kudos to everyone, basically the speakers, because you basically give all the contents and all your hard work for us, and all the community that have been watching this. Also, a big thanks to Paula, who have been doing a lot of organizational work for the conference together with me. Also, I would like to thank r2wars, who have been managing all the stream and all the games that have been and reviewing all the bots and so on, which is quite hard work and a lot of fun also. So I've been also working with Squadron for the r2wars competition. For the CTF, it was Murphy, but there was like many other people behind the scenes also writing all the games and crackmes. Also, I would like to say thanks for the workshops. I'm missing Tim in the list. Well, Tim did an awesome SMT workshop, and Edu, Exploiter, and Murphy did the R2 training. I will also like to say thanks to the Sergi and Danito, who are the ones behind the Camisetas Frikis company, who is the ones that are building and manufacturing all the merchandising that we are shipping to all the speakers and Google Summer of Code students, as well as all the winners in the games. And finally, I will like to give a huge thanks to all the artists that have been giving away all their work for the music that we will be having fun and enjoying after the keynote. So basically, all the music that you have been listening during the breaks in the conference was done by them. So you can see, this is the names if you want to Google them or find some more details on this, but you will be able to follow all the Chiptune concert that is happening right after this keynote. So it's thanks Wiklund, thanks Klirre, thanks For the Boy, thanks Edge, thanks Neuroflip, and well, basically thanks to everybody who have been using our tool, developing, contributing, following the talks, the stream, giving their feedback, checking out all the stuff that we are doing, and also contributing back with the games and all that stuff. So it was an amazing conference. It's probably the best conference that I've been online. I've never been organizing any of these before, and it's been an amazing experience for me, learning a lot about streaming. There was a bunch of mistakes in real time, but hopefully we will learn from all this stuff or improving on future editions. So we will be sharing a form, so you can give us some feedback on all the stuff that you have been seeing during the conference. This is the link. It's embedded in the website, so you can check out the website of the conference. And at the bottom of it, there is like another form, not just the one for the merchandising, and you can give us some details on ideas or comments about the stuff that you have been seeing about the conference. So thanks for watching, and yeah, after a short break, we'll jump into the Chiptune concert. So thanks, everybody.
Hello everyone, thank you for tuning in to this amazing stream and event. And so I'm Wiklund, and once again, thank you for tuning in, and just keep watching because it's amazing art. Oh, hello, I was talking to myself. Shit, it was muted. Well, I want to say thank you for tuning in, and thank you for listening, and thank you to all the organizers for creating such an amazing event during the pandemic. And stay tuned because more amazing music is coming from such amazing artists. So just stay here and listen and enjoy all the music. Bye guys, you're the best.
Thank you very much. The show is over. Thank you. Thank you very much, especially to Pancake and Paula. They are the organizers of the event. And to all the audience and to all the artists too. And well, you are awesome. Thank you very much.
Hello, I'm Edge, and tonight we'll play Chiptune. Thanks to Fordy Boy who was playing before, and Klirre and Wiklund before that. You were doing awesome music. Okay, let's go. I guess it's our first crash of the night. Just let me try again. My Game Boys really don't like that song. It's too powerful for them. Okay, we're good to go again. Thank you. It was the end. Let me just grab this. Oh, so thank you for coming to that r2con online chiptune party. Thank you, Pancake and Paula, for organizing all this and all the other artists. Next one is neuroflip. And if you wanna support me, you have all my links on the left. You can search me on Bandcamp at 3D63. And thank you. So see you later. Bye.
for the Chiptune party at fucking 2020. There's a lot of Game Boys tonight, so let's get fun with some Amigas.